Hi everyone, I'm Jeremy Daly and you're watching the second edition of Serverless Days Virtual. So if you have never been to a Serverless Days conference before, you are in for a treat. Now these are typically these locally hosted events. They're all around the world. It's all about fostering community around serverless technologies. Each one of these events is unique and it's organized by locals, completely nonprofit. So we are doing something different. Obviously, the coronavirus, COVID-19, has affected all of us, and most of the planned events for this coming year, or this past year at this point, have been canceled. So some of them have been virtual, some of them have been rescheduled to next year. Hopefully, when the world gets this virus under control and everybody can go back to hopefully coming back to some of these conferences, we'll be able to meet again. I am wearing my Serverless Days Boston t-shirt. We had to cancel Boston this year, but again, hopefully next year we're going to be able to do it in person. Like I said, these are great events. It's a really good way to connect with people, especially in this niche community right now of serverless. So hopefully we'll get a chance to do this soon in the future. We'll be able to get together. And when you do that, I definitely recommend that you take the chance to do that. Anyways, in the meantime, because there are so many people in this amazing community that love serverless and want to keep educating and keep pushing it and make sure that as many people can use serverless as possible, there have been a few dedicated serverless fans who have said, you know what, we're going to make this thing go anyways. That's Ant Stanley, Farrah Campbell, Gunnar Grosh, and Emra Shamdan. They are the ones who are making this happen for you right now, so thank you to them just for putting all this stuff together. There is a huge production going on all across the world, and it is very late at night for those in Europe and Turkey right now. So they are doing us all a great service by staying up and pulling a serverless all-nighter. So we have a very packed schedule today, about 4.5 hours worth of content that's coming your way. We did put in a number of breaks so that you'll have a chance to get up, grab a coffee, or your beverage of choice, and give you a couple of minutes in between talks. We have all of our speakers are going to be live with a Q&A, so make sure you stick around after each talk to listen to that Q&A. If you have some questions, we do have a Discord channel set up, so you can go to virtual.serverlessdays.io, and you can find all the links there. It's discord.serverlessdays.io will get you to the Discord channel. You can talk to the speakers, you can ask them questions, and then after that, we'll try to ask those questions for you and get those answered. So that you can get all that information that you need. So again, packed schedule. We have Adrian Cockroft, we have Linda Nichols, we have Rusthem Feyzkhanov, we have Richard Buggy, Will Velida, and Denis Bauer. So there's just going to be a ton of serverless content coming your way. So stick around, get comfortable, settle in, because this is going to be a lot of fun. All right, so before we can get into the talks, though, we do need to go through a couple of things, especially if you're going to be using the Discord channels. Okay, so Serverless Days is all about being inclusive and accepting to everyone. Everyone is welcome in our community. So we have a code of conduct that's posted on the site, and you have to agree to that if you want to participate in the chat, and we'll have some moderators in there as well to make sure that it's a safe space for everybody. So here are a couple of rules to remember. Number one, be nice. All right, we are, this is not hacker news. All right, if somebody asks a question, there are no bad questions. Everybody's learning here. There's lots of new things. We want to make sure that everybody gets a chance to ask a question and feel safe asking those questions. Let's not spam, all right? So no advertising, anything that's not safe for work. Don't be rude. Don't be annoying. Don't get into prolonged, heated arguments. Twitter is for that. If you want to do that, take your discussion to Twitter. We're going to try to communicate in English. I know we're doing this, we're targeting, the APAC right now, but we do want to try to communicate in English using the chat. That way everybody can, everybody around the world hopefully can have a common way to communicate there. No advertising and no DMs for anybody advertising something else either. Please avoid offensive usernames or nicknames, so just please choose something that is appropriate. No self-bots, no user bots. And then we have a bunch of channels set up. So we have a channel set up for each talk as well as a hallway track. So if you want to ask questions about a particular talk or to a particular speaker, try to bring your conversation in there. And then if you just want to kind of talk to the other attendees, then use that hallway track to do that. So the speakers will try to answer those questions in each of their rooms. And if you have any problems, just reach out to Ant, Farrah, Gunnar, or Emra, and hopefully they can take care of any of your issues. And of course, the most important thing is have fun, learn about serverless. It's going to be amazing. We have some really, really great talks coming up. So I know I'm going to enjoy it. I hope you enjoy it too. All right, so to get us started, we have the Vice President of Cloud Architecture Strategy at Amazon Web Services. That is a complex title, but Adrian Cockroft has been talking about serverless for quite some time. If you want to learn about cloud architecture strategy, this is the person that you want to learn this from. So his keynote today is about modern application development and why you should choose serverless first. And I agree. I think you should choose serverless first every time. Anyways, here is Adrian Cockroft. Adrian, the floor is yours.
Okay. Am I online yet?
You're good to go.
Okay, cool. So we've got serverless, and we've also got officeless, and now conferenceless. So we're just having to figure out how to run all these things from home. Hopefully everything stays on, and I can get through my deck and some talks, some discussion afterwards. So I'm going to talk about why I think you should always start developing pretty much anything serverless first, anything new, certainly. And also some of the kind of workloads that it's been used for. But most of my talk is really ammunition for people that people like yourselves who may be already into serverless, to go through all the reasons why people give you objections. So there's objections and objections for why people say, well, I'm not going to do this. So I've got the second half of my talk is just a long list of objections, and I'm sort of playing whack-a-mole with them, sort of knocking down each one as they come up. So to start off with, let's just take the base here. This isn't an incremental change, it's a complete reset. The speed of development, the cost and the scalability of what you can build is just it's not an incremental change. It's not 20% better than the previous ways of doing it. It's 10 times or 100 times faster or more scalable or bigger. So it's a really different model. So let's think about how long does it take to build a new application from scratch. And I want to go back to something that we do at reInvent, had for many years, a nonprofit hackathon for social good. So you get teams of 4 people. You come in on Monday morning at 8 a.m. There are 4 nonprofit organizations. You get assigned to one of them. That organization describes a series of problems they have, and the team has 12 hours to basically come up with a solution. So if you've got 12 hours from beginning to end, from a cold start, and there's only 4 of you, what technology are you going to use to actually build this? How would you start? Turns out it's mostly serverless. So soon after I joined AWS in 2016, I was at reInvent, and they asked me to be a judge at the hackathon. And this is really early days, 4 years ago. Every team used Lambda really in half a day, and many of the team members, for the very first time using Lambda, they built extremely functional, scalable prototypes. The people from the nonprofits, some of them were just like, how could you possibly have built that in a day? It's ridiculous. And for me, it was a light bulb moment that you could build things that scaled and were reliable and very functional in an incredibly short period of time. So I started telling that story to people, and people started telling stories back to me that sounded similar. So I've got lots of anecdotes, and I'll just go through one. I've got a few of these. This was a good one. It says, okay, we had 20 people, we had 9 months, and there were 2 months left, and we really had made very little progress. We'd sort of defined what the problem was, but we were a long, long way for building it. And everyone was getting pretty annoyed about this. And there was, a couple of people here going, there must be a better way. So what happened was, it was Friday, they were getting lunch, getting a coffee or a beer or something, and feeling pretty depressed about what was going on. And then one of them said, well, I'm sure we could rewrite this whole thing, serverless, in just like in a weekend. What are you doing this weekend? Well, I'm not doing much. I can get my family to go away, or I've got a quiet weekend. Let's just spend the weekend and work through this. And this one of these two people was chatting to me and telling me the story. So they just worked through the weekend and they just, ate and slept and coded. And around midday on Monday, they basically had built the entire thing, the whole of the project, every piece of functionality. So then they went into the office, and then they spent the next month persuading everyone else in the office that they had actually finished building the whole functionality and that this was secure and it was possible to deploy it. But a month after that weekend, they actually deployed this application. So they ended up deploying a month early. Now, that's, two people solidly for a weekend isn't normal working practices, but think of that as probably 2 or 3 man weeks of normal, person weeks of normal activity, normal pace work. But it's certainly not 20 people for 4 or 5 months. So it turns out a lot of corporate IT apps are very low utilization, spiky workloads, complex business event handling logic and workflow. And this is the kind of thing that is really ideal for rewriting to serverless. You can take a lot of these things and go very quickly because it's really a good fit for this. You don't have to go building all of these different pieces to work around these problems. They're inherent in the way serverless works. So why is it so fast to write a serverless app? And I have an analogy for this. Let's say we want to build a suspiciously familiar looking toy spaceship quickly and cheaply. Traditionally, we'd design a prototype, we'd carve some modeling clay things, we'd make some molds, we'd produce a bunch of injection molded parts, assemble the parts together, find they don't fit, go back and rebuild the parts a few times, go around that loop for a bit. And in the end, you've got a finished toy and you can mass produce it in volume very cheaply, and it's very efficient if you want to thousands or hundreds of thousands of them. So that's the normal way traditional development works for software as well. So for rapid development, you get a big bag of Lego bricks, you get the instructions, and a few hours later, you've built yourself the entire thing. But it's obviously not quite as shiny. It doesn't have the fine detail. You had to compromise on a few things. It isn't exactly what you asked for. But it's easy to modify and extend, much easier to modify than the molded plastic one. Then the other thing you can do is say, this part just isn't pointy enough. I'm going to make a new custom brick. And if you look at the history of Lego, they started off with some very simple bricks, and now they have thousands and thousands of pieces, and many of the pieces are nose cones or people's faces or hands or things like that you couldn't build out of bricks. So you've seen Lego take this model. And in fact, Lego is actually a big user of serverless, so this is actually an extra resonance on this example. But what you're building here is a specialized common component, and you're using it as a late binding optimization in your development flow. You've done your build, you've got your prototype, you figured it out that was the thing you wanted and it's roughly the right shape. Then you just start working at the rough corners and the things that didn't work quite right. So if we compare traditional versus rapid development, instead of full custom design, we're using lots of building blocks. But it really is months of work to hours of work. The custom components can be fragile, reliable components are well understood. Lego bricks, you know how they fit together. They were, Lego bricks from a decade or 20, 30 years ago, they still work. The other thing is that traditionally there are too many detailed choices. You can spend a long time making up your mind of exactly what you're trying to do and discussing how to approach it. When you've got more constraints, you actually go faster. So you have to adjust your requirements to fit the patterns that are available, but the constraints reduce debate and speed up decisions. And it's a counterintuitive thing that the more freedom you have, actually the longer you will take to build something. There's a lot of value in having constraints in the system. And if you take this to be sort of containers and serverless, then obviously with serverless, we'd build it using all of these building blocks. But sometimes those building blocks don't quite do what you need them to do, or they're not quite efficient enough if you want the large scale thing, like the 10,000 models of the spaceship kind of idea. So you want to tune something and build a container-based service to replace something that you prototyped using a bunch of Lambda functions. So that's kind of the idea here. You rapid prototype, you build a quick thing. If it's a bit clunky or the latency is a bit high or it didn't quite fit, then you reluctantly go and build a custom service using containers to go build that out. But most of your work remains as serverless. So why doesn't everybody go through the objections and the limitations? And I categorize them into these 10 areas. And I really have answers to all of these, so I'll go through these one by one. Let's start with programming languages. To start off with, Lambda was node only. And PowerShell and Go, Python, Ruby, C#. There's also a C++ bring your own language runtime API that we open sourced. So the example for C++ is an open source toolkit. That lets you plug in any language you want. Now, obviously, if you compile down to the JVM, Clojure, and Scala, those just work with Go anyway. But languages like Rust, PHP, Erlang, Elixir, COBOL, and Fortran have been built using the Bring Your Own Language Runtime API. So if you have an internal custom language that you've been building everything in, RPG or something, or some weird language no one has ever heard of that was totally internal to your company, you can actually use the Runtime API to build it really quickly. It's not a hard job to do this. Here's another objection. When it started, it was pretty small scale, and the default execution limit was 100 threads, so you could have up to 100 Lambda functions in parallel, and then the system would stop scaling. The default is now 3,000 CPUs in Virginia, Oregon, and Dublin regions, and between 500 and 1,000 in the relatively smaller regions around the world. That's the default. If you talk to us nicely, put in a service ticket, something like that, we'll go a lot bigger than that. So you can actually limit this to tens of thousands. So think about having, say, 50,000 or 100,000 CPUs just ready to go with a Lambda function in them in parallel. That's an incredibly large scale system. It's a supercomputer scale system. Here's another thing that we've been running into. The per function maximum disk space for a long time was 0.5 gigabyte. If you couldn't package up that data into your system, then you couldn't send it, you couldn't create a function around it. So people would create container-based workloads for things that had a larger payload. And we just recently, in June, announced this option where you can now have EFS. So basically your Lambda function will NFS mount a file system which can be petabytes in size. You can now have almost 50 terabytes per file, and the Lambda function can access it. Kind of thing this is useful for is machine learning models, where the output of the model can sometimes be several gigabytes, and you actually want Lambda to load that model and run with it. Or maybe there's just a big data set, and the Lambda function needs to pick a few pieces out of that data set, but doesn't need the whole thing. But you don't want to slice it into chunks up front. Up to 25,000 concurrent connections by default into EFS for a single application. So that's pretty powerful and scalable as well. Another common complaint is that startup latency is too high. This is another area where I think you should just try it first to see what happens. And we've had years of performance tuning to speed it up gradually. So if something that you tried a year ago was too slow on startup latency, try it again. Both the average latency and the 99th percentile have both been reduced quite a bit over the last year or two. We've also now got provision concurrency. So a Lambda function has an initialization phase. And for languages like Go, it's really short. You don't really need to worry about it too much. But if you're running in a JVM or something that loads lots of packages, maybe JavaScript or Python, you've got an interpreter and it's piling in all of those NPM modules, you can get it to the point where you've run all of your initialization code, and then the system stops and runs multiple functions from that point. So what you can do now is do provision concurrency and tell us you would like to have 100 or 1,000 or 10,000 or more pre-initialized functions, and you tell us a few minutes in advance of your flash sale or your add-on TV or whatever it is you're worried about. And then we preset them up, you run them, then you shut it down. So you can have this set up in advance and have it running for an hour or two or whatever you need. You can scale it up and down. So that basically gets you around that initialization latency. Very useful for Java applications, I think. Another thing you'll find, particularly if you look around at examples from a year or two ago, a lot of people complaining about the time it took to start up Lambda functions that were on a VPC network. And that was because these network adapters were designed to be initialized at the pace that you would create an EC2 instance. So it didn't matter if they took a few seconds. What we did was we tuned it to be basically instant. It doesn't take very, very long now, and you don't need to worry about it. So you can attach to a VPC basically as fast as you can attach to any network. That really only came in September last year, so if you run into that problem again, try again. Anytime you run into a problem, you have to keep retrying because we're moving so fast here. Another complaint I've seen is that when people look at their bill and they say, well, my Lambda cost X, but the API gateway calls that got to the Lambda cost more than the Lambda functions they were calling. I mean, and both numbers are still mostly pretty low numbers, but it seems kind of odd that the gateway costs more than the code it took to run. There's a few things you can do about that. One is that we reduced the cost of API gateway late last year, and we also put in there's also sped it up a bit. But Gateway is incredibly powerful. You can do extremely complex transforms. You can throttle things. It's a really powerful processing stage in your pipeline. It's not a simple routing system. Because if all you wanted was to take the slash whatever path in your URL and send it to Lambda function named something like whatever, you can do that using an ALB. So if you want simple rules, high throughput, lower cost, you can just use an ALB to route to Lambda. The other thing with applications which have a very expensive API gateway is you probably could redesign the API. And that's what GraphQL lets you do. You send in a single query, and when it hits the Lambda function, it explodes into all of the individual pieces of data that you're ever going to need to, say, build the entire home page for a complex application or a mobile application that's starting up. You gather all the data, you put it into this graph, and GraphQL returns it in a single shot. So your round trip to the cloud is a single request and single return, but you can have an arbitrary complicated thing that is built as needed as you run the system. So that way you've got many fewer calls going through and your gateway costs will also be less. Here's another objection, security. Now, we actually nowadays, for about the last year or so, we've been running every function in its own virtual machine. So that gives you a minimal attack surface. What we did earlier is we had one virtual machine per customer. So none of your Lambda functions were shared with any other account. But we would have a single virtual machine that would run multiple Lambda functions for the same account. So what we've done with Firecracker is we've given a lightweight virtual machine for every individual Lambda function that gets invoked. So that gives it a lot of lockdown capability. The other thing is, if you pre-initialize a Lambda, it's only reused for the same account, the ports. The attack surface is really small. And the other thing is, initialized functions are recycled after a few hours. There's no long-running services to get infected. You might remember a year or two ago, there was Meltdown and Spectre, and there was a big announcement about it, and everyone had to run around patching. We sent out an email to all our customers, and we said, here's where you get the pre-patched image, operating system image for Amazon Linux. Here's where you get the EC2 AM machine image, the AMI. And here's where you get your containers that are pre-patched and everything like that. And if you're running serverless, don't worry, we took care of it yesterday. You're fixed. Just carry on with your life. And that's really the benefit of serverless here. Another thing that people think about is that Lambda functions in practice are supposed to be, the whole point of Lambda calculus is that it has no side effects. It's functional programming, and it's hard to handle state in functional programming. So there's this sort of idea that Lambda maybe doesn't handle state, but it turns out that you can obviously hard code state in, because even fully functional programming languages have some way to manage state. But with step functions, you've actually got a complete state machine that's incredibly powerful, and you can create will last for a year. This is very useful for interactions that involve waiting for people to do things, like you send them an email and you're waiting for them to get back to you. Like those email confirmation steps where, into your web email here, click the button, it sends you an email, you have to click on the email to confirm. That could happen weeks later. With step functions, that could happen up to a year later, and all the state is still there, everything will continue. You haven't lost your session somewhere in the system. And again, lots of interesting things you can do with this, and lots of business workflows. In fact, we're almost getting to the point where you could say step functions first rather than just serverless first, because I think there's a lot of things that you can build by starting with step functions and then building out Lambda functions for the individual steps. It also has a way to visualize what your business logic is, and we're getting a lot of feedback from customers, again, on the various things that this does well and the areas where we need to extend it. So this is also moving very quickly. Now, this is also something, first incarnation, it was pretty slow. Now we have step rates that are pretty high, cost per step's been reduced, and then we recently came out with Step Functions Express. This is for a workflow which will last for a maximum of 5 minutes, but it'll run over 1,000 events per second. So the idea here is you might want to stream everything out of one S3 bucket into another S3 bucket, or whatever you want. Maybe in a lot of data science workflows, you want to use step functions, but you want to pump a huge amount of data through and process each piece of data separately. That's the kind of thing that you can do with this. Now, running for longer, 5 minutes, pushed it. We asked around, everyone said, yeah, 10 minutes would be enough, plenty. 10 minutes would be plenty. So we gave everybody 15 minutes, and then people said, actually, we want more than 15 minutes now. There's always going to be some limit here. That's the point of the service. Otherwise, we wouldn't be able to do things like automatically patch the servers that are underneath. So always think that these instances are going to go away and be recreated. So this is one of the cases where you might want to use AWS Batch or Fargate to create serverless containers for long-running jobs, to just make sure that if you've got something that really needs that persistence, or it's just going to run for a long time. So this is one of those cases where we don't quite support this workload that well. But you could certainly build a prototype and to make sure that you've got the flows working right. Another case is where you want specific hardware. You can't really tell Lambda that you want to run on an instance that has a GPU in it, certainly not yet. And if you look at GPU hardware, it's pretty heavyweight. There's a lot of memory there. There's a lot of initialization time. So we have to work out how to build something here which is really fast at being virtualized and shared. Now, there is a GPU variant which we have virtualized for EC2. So we're kind of part the way there, but we don't really have this as a supported mechanism right now. So this is, again, another place where if you want to run 5 or 10 minutes of baking your doing a deep learning model training, then that might work. Yeah, but typically these kinds of things are very big and they run for hours. And for the inference side as well, that's where I think this gets more interesting. We might actually be more demand for doing this. So if we look at event processing, there's some pretty sophisticated ways of doing this, and really I haven't spent enough time with these to really know more than scratching the surface of what these do. You'll have to dig in. There's lots of reInvent talks on this to go look at, and there's an open source connector for Kafka that I've got a link for as well. So there's data streams for Kinesis, there's SQS and SNS dead letter queues. You can build all that. Lambda destinations. The idea here is that if you want to talk to DynamoDB, you don't need to create a Lambda function that talks to DynamoDB. There should be, DynamoDB should just be a destination that Lambda knows how to call. So what we're doing is we're gradually taking all the services that AWS has built and building a Lambda event destination into that service as a default part of that service. That's another sort of pattern you could build for your own services. We've got detailed controls for streaming and asynchronous events. And then there's Event Bridge. You can use this to do a one-to-many fan-out. So when an event hits an event bridge coming out of one Lambda function, it fans out to lots of Lambda functions. And then there's also, particularly with step functions, there's this sort of scatter, and then there's a gather back together where you can create a step which waits for all of the fan-out to come back in to sort of map it back together again. Now, when we talk about talking to SQL databases, they quite often have connection limits. So there's a number of database threads or connections that is configured as part of the database. If you just make all your Lambda functions talk to that, you can easily overrun a typical database configuration. So what you use is a per function concurrency limit to prevent Lambda from overrunning those interfaces. But we've also now got an RDS proxy for the major databases that we support, using Secrets Manager, and it does all the pooling and failover. So it's really easy to use and keeps those credentials out of your application code too. Now, if you're getting a lot of Lambda functions and a big complex use case, lots of people working on a project for a long time, you may have hundreds or even thousands of Lambda functions. You need ways to manage at scale. We're getting into that as well. So we have Systems Manager Parameter Store. You can use that for controlling sort of the environment variables and feature flags that you need for tuning and configuring your system. You can do A/B testing and versioning and things like that. And then also KMS for encryption integration, so you don't have any hard-coded credentials. So KMS is the key management system. I put a link in there to a comparison of when to use Parameter Store, when to use Secrets Manager, and how that compares to tools like Vault, HashiCorp's Vault, which is another KMS. And we've also got Lambda layers. So if you're finding that many of your Lambda functions share the same boilerplate code underneath because you're sort of building platforms as you go along, you can use Lambda layers to stack up those platforms. It's a bit like what we have for Docker containers, where a lot of the code is common. So portability, this is really one of the main reasons that I hear from people saying that they don't want to use serverless. Well, if you can build something so quickly, maybe you just build it twice. You build the Lambda version and you build the Azure or Google or some other version. And you've still spent less time than if you built the fully portable container version. So I think it's worth building serverless even if you have to build it twice and even if you have to do a port, because you can probably build it in less time than you'd spend arguing about Kubernetes overall. It's a bit of a flippant comment, but I've had a few people sort of nodding in the audience when I've made that argument. If we look at other portability tools, there's a lot of open source projects now around serverless in general and around Lambda in particular. So I've listed a whole bunch of them here. And if you want to build and look at other serverless frameworks, there's things like Trigger Mesh, which is reasonably Lambda compatible, but running on top of Istio, Knative, and Kubernetes. There's a whole load more Kubernetes related, things like OpenFAS and Kubeless. There's Apache OpenWhisk, which is a whole serverless framework itself that IBM built. And then there's Azure Functions and Google Functions. So all of these different frameworks and things like the serverless framework gives you a way to sort of port across these different things. If we look at debug tools, here's another objection. In the early days, it was pretty hard to find tools that understood serverless. But now there's a long list of them, and including the mainstream tools that have been around for a decade or more. They all support serverless now, and also much better support within AWS. And the X-ray integration is particularly important because we can look under the hood and see exactly what's really happening to the serverless function and measure the invocation latency. That, you don't have to use the X-ray tool because there's an interface for getting this data, and that data is then fed into tools like Datadog and IOPipe and all of these other tools. So they're using the X-ray as a data source rather than using the X-ray user interface over the top of it. Now, we're all familiar with patterns. The patterns books go back 20 years or more, and a lot of people know their Java patterns. But what are the serverless patterns? Well, we have Jeremy Daly's done a good job of, in the patterns blog, going through listing all these, and he's, all the standard patterns you might have heard of, like circuit breaker, strangler pattern, webhook, all the GraphQL, all of these are detailed. Another pattern you find on serverless, it's not really a pattern as such, but the power tuning test helps you figure out exactly what parameters you should be running for the sizing your Lambda function. Like how big should it be? How much memory and CPU should you give it? And it's a little counterintuitive because quite often giving the Lambda function more capacity lets it run so much faster that it actually uses less resource. So using the minimum options for Lambda is a common problem that is an easy fix for. How about getting started? Well, we've got the serverless application model, SAM, templating, roles management, trying to make it easier. We've got CDK support for serverless applications. And we've got the serverless framework and also Terraform support for configuring everything. And we've added a lot of the things to SAM CLI recently. Another thing people want is local support for testing with Docker containers. We have all that support with SAM as well. So you don't have to be connected to the network. You just play around on your laptop for just testing simple functions. Now, we've also got this thing called the serverless application repository. The best way to think about this is pick your favorite SaaS vendor. How should they interface to serverless? Let's say you want to connect to Salesforce or Splunk or something like that. You go to the serverless application repository, look up something like Splunk and find that there's a serverless function in there which knows how to talk to Splunk. You can include it in your application as a building block, and more, if you are a vendor of a SaaS application, you should get your application in here. So it isn't really a marketplace in the same sense as the AWS marketplace where people are buying and selling serverless functions. It's more interesting to be a gateway into pre-built applications, pre-built services. I'm going to run very quickly through a demo application built by Jerry Hargrove. There's a version of this available on GitHub if you want to go look at it in some more detail. So he started off saying, what kind of plane is this? And he built a simple bot to do that. The idea was you tweeted a picture of a plane at the bot and it would try to guess what kind of plane it was. So a Lambda function should tell you this is a 380. That sort of worked. Evolved over time, got a bit more complicated, got a few more things in there, and got a bit more code. And then finally became a real modern, interesting application. And this is the structure of a lot of applications. We've got step functions at the center that's coordinating and operating the business logic. The individual steps in the business logic are either off-the-shelf services or they're Lambda functions. Orchestrated with step functions, control flow, all the error conditions, looping and branching is all in step functions, and then the individual steps of business logic put into Lambda. Some example, he wrote it all in Python. There's a bunch of code here. And well, the step functions piece is all in Python, and the CDK, this is actually the CDK part as well. So you can go look at his code to see how we put all that together. So just to wrap up then, there's answers to all of these things, I think, and hopefully this is useful to serverless fans to go out and next time somebody says, hey, this is something I don't like, you've got top of your head, oh yeah, go find that slide, or remember this is the answer to that particular objection. And I think serverless really is the fastest way to build a modern application. We've seen all kinds of people doing it. We're seeing people replacing mainframe COBOL with serverless, as well as building completely new applications. We've got some startups that are 100% serverless, and we've got some of the largest, oldest companies in the world transforming some of the oldest applications in the world with this. So again, if you find something that doesn't work, that wasn't on my list, let us know, because we're probably already working on it, and we should figure out what to work on next. So that's what I've got. Happy to do some Q&A. And I did not manage to get hooked up to the tool. So maybe you can sort of read some questions to me, and I'll answer them.
I can. First of all, thank you, Adrian, for the talk. You've got me convinced. Although I've been a serverless person for quite some time. But wonderful talk. And there are a few questions that I have, because I think it's super important when people are starting to develop with serverless. And again, you went through all these objections, and that's great. Something you mentioned early in the talk, though, was this idea of there being value in the constraints. And I really like that idea, because I feel like serverless forces you to think a different way. Can you expand upon that idea a little bit more?
Yeah, this is sort of an architectural principle, really. Kind of the mistake a lot of people make is they make it too complicated and you over-specify things. So some of the more persistent architectures, the things that last longest, actually have a simple architecture that's under-specified. So that's kind of a higher level way of thinking about it. And then if you look at the actual sort of discussions, I've just seen people spend forever, months later, they're still evaluating design specs for, which vendor they're going to buy Kubernetes from, or whether they should run Istio or not, or all these layers and layers of control planes and all this kind of stuff. And it's, there's certainly, you can get into a much easier, more packaged approach with something like Fargate or with EKS or one of the Kubernetes as a service patterns. But still, there's a new version every 6 months. You've got to pick the version, and this thing doesn't work with this version. You just go round and around a lot. And I think with serverless, a lot of concerns just go away. You can get on with, like, what problem was I trying to solve? What's the business need? How do I make customers happier? And you can just deploy the thing and build it and see where you are.
Yeah. No, I love that idea. I know from my own experience, maybe 10 years ago now, I was building an application that needed a real-time chat component. So we were thinking of WebSockets, long polling, and we researched a whole bunch of things, ended up installing some, out-of-the-box software, and then had to customize it. Now it's basically, do I want to use AppSync, real-time communication, or do I want to use WebSockets with API Gateway? And even though there might be some limitations in there, that decision is easier, and it's just so much faster. So love that idea.
You just talk to the Slack API or something like that. I mean, these chatbot things exist as an entire platform now. Right. You don't have to build it into your app. This is one of the other reasons why serverless is so fast. The stuff you used to have to build is just now available as a SaaS application. And you should be gluing together all these incredibly highly functional applications. You're standing on the shoulders of an army of giants when you do that, rather than having to code everything yourself.
Right. All right. So another thing, we're talking about serverless now, and I think some people haven't even moved to the cloud yet, right? And some people haven't even made it to microservices yet. And I kind of have this question around microservices and serverless, right? So microservices, I think that's becoming more and more familiar to people. It's been around for quite some time. Obviously, AWS has been doing it for a while. When we're building serverless applications, should we be thinking in the microservices mindset in terms of bounded context and not sharing databases and things like that? Or does serverless change that a little bit? Like, how does that architecture maybe differ from microservices? Or are we just using smaller functions but still staying within that bounded context?
Yeah, I mean, you can abuse anything to do just about anything, right? So you can certainly build a monolith and run it as a Lambda function if you really try hard. But the way that it naturally seems to work is that if you look at a monolith has too many different things in it, and it's just too hard to manage. Once you get over a certain size, and once you have more than a few people contributing to it, they just naturally get tangled into a big mess. If you split that up into microservices, the idea of a microservice was that it was the API should do one thing, right? It should be a noun or a verb, right? That's the idea. And if you go down to and look inside a microservice, it probably has several functions in it. Some microservices are just single functions, in which case you can just build the Lambda version of it. But in many cases, there's like the normal function, and then there's some different thing that happens occasionally, and there's a whole bunch of functionality which is only used occasionally, right? And if you think about the memory footprint of a monolith or a microservice model where all the code and all the initialized logic that is only used occasionally is sitting there in memory, not doing anything, your memory footprint is overblown. And when you have Lambda functions, that thing that's invoked very infrequently, maybe it's an error handling case that rarely happens, right? All the memory footprint of that is just not running. So what you get with splitting down your microservices into the individual functions is that you get another level of efficiency of memory usage in particular, right? And then you get the on-off efficiency of the, whenever it stops doing, whenever there's no work to do, it goes away. So, and there's certainly quite a few code paths in systems that are not busy all the time, not enough to keep a CPU busy all the time. So that's the way to think about it. I would look at it as partitioning a microservice into the individual functions that make it up is the sort of the purest form of doing it, of building a serverless function. And a serverless function is, the bounded domain should probably be a group of functions that work together, and maybe that's sort of a little bit larger. And sometimes it's a group of microservices too.
Yeah, and I love the individual function saying I can just scale my image processing function, even though it's part of a larger microservice, but I don't have to scale everything up. And then of course you get the security, and you can do the principal of least privilege for each one of those functions too, and really lock that down. So that's awesome. All right, so another question I have: you mentioned GPU. If you have a workload that doesn't fit into serverless, and you're thinking about maybe I need a GPU, or maybe I need it to run longer than 15 minutes. One of the topics that's been coming up quite a bit, and Tim Wagner actually brought this up, was this idea of the Lambda supercomputer, right? And so I know some people have been poking around with different things in Python and whatever, and having Lambda functions actually talk to one another and coordinate behind the scenes. I know the AWS probably thinking well into the future, but is this something that you see Lambda eventually going to, where it would allow you to do some of that sort of parallel processing in a more coordinated way?
I think there's a combination of things here. There's hardware and software and demand, right? All these different things. What are you doing first, right? NVIDIA just announced a new GPU which supports natively multiple VMs. That's the first time I've seen that, right? So the hardware is starting to appear, that's just an announcement at this point. So there's the ability to do more fine-grained access within a GPU, and the virtualization support within GPUs. We have our own custom GPUs we're building now as well. So I think the ability to do it is coming, but the hardware is not quite there yet. So that's the first thing, because you really want to be able to hit a GPU, go through the initialization phase and hit a GPU and do an inference in milliseconds, right? You want to be able to recognize the face of who's at your house, doorbell, whatever it is, if you're trying to do those kinds of things, or you want to be able to classify something that's, on a conveyor belt, all those kinds of applications. Those classifier type of applications are great for Lambda functions, but they'd need to be, and they do run now, they run well using just the Intel accelerator that's built in. I mean, the Intel processor is pretty good at running deep learning models on its own, and you don't have the overhead of having to move your model and your data into the GPU and back out again. So that's kind of, there's a point at which the duration of what you're running gets to the point that it's worth putting it into a GPU. So there's a few different trade-offs. I'm sure it'll happen eventually. I don't have any announcements or anything up our sleeve, but there's quite a bit of, there's a lot of interest in deep learning, and we're seeing a lot of use of Lambda in deep learning, but it may be just you call the recognition library. I mean, we have all these services that, or one of the many different APIs that do deep learning for you, and that's probably the main use I'd see right now.
Yeah, I'd love to see that, though, with those the idea of things being more coordinated, or the GPU would just open up a whole nother level of use case, and you can add more things to your objections at the end of your talk.
I'm hoping to add a few more objections. If people want to send me that, I'll get on the Discord eventually. Once I'm off the call, I'll stay on the call for a bit, on Discord for a bit. And over time we'll just play whack-a-mole with some more of these things that it doesn't quite do yet.
Right. Great. All right, Adrian, thank you so much for your talk. Thank you for letting me pick your brain here. So for our listeners, we are going to take a 10-minute break. We'll be back at the top of the hour with Linda Nichols.
All right, thanks very much. Cheers.
Hey everyone, welcome back. I want to thank Adrian Cockroft again for that awesome talk, and hopefully you are all convinced to start all of your new projects with serverless first. Our next speaker is a technical specialist at Microsoft. She is also the only person I know who I think is a cloud black belt, or maybe work for the black belt team. Excellent speaker, always fun to listen to, great late 80s, early 90s references. So here is the talk, Serverless to Codeless, from Linda Nichols.
Hi everyone, happy to be here today, and I'm going to be talking about from serverless to codeless. And I'm coming from a developer background, but I'm going to be talking today about not writing code, or at least not much of it. I'm Linda Nichols, and I work for Microsoft. I'm a technical specialist on our cloud native global black belt team. So hello from the year 2020. We've all survived, over halfway through 2020. And, it's all uphill from here. So I'm going to start out with a couple quotes that are relevant to going codeless or writing less code. And the first one is, the only thing I like better than writing code is not writing code. Which is from Travis Webb, who is the co-founder of Norfolk.js, which is a JavaScript user group that I also co-organize. And this was just from some talk not even related to writing code or not writing code that has kind of stuck with me and a lot of other people here locally, because it's sort of the last thing you'd expect to hear from a developer. And yes, just like we have better rockets than the Coyote, we also have many services now out there to support us as developers and serverless developers. So let's talk about a little bit about the before time. And the before time wasn't all that long ago. I definitely remember this, and I'm sure many developers do. But this is back when being a developer meant identifying as a coder. Your language, your style, arguing over things like, spaces and tabs and semicolons, and, really like dying on these small molehills, because that was just part of being a coder. Your job was to write a lot of code, and to, solve lots of problems and be clever. But now, really a lot of the code that needs to be written to solve problems has already been written, either in the way of open source, or perhaps, it's some like external service within a cloud platform or some other platform. And really, writing good code isn't as important as it used to be. Now using good code is more important than actually writing it. And, as we move on to the future, really what's going to become really important is iterating very quickly, and innovating, and not about code at all, and certainly not about writing lots of code, because as we're discovering, code is expensive. Not only does it take time to write code, and time is money, but also every single line of code you write is a potential defect. And that means that you have to write more tests to account for defects, and all that becomes money. So as we stop becoming coders, it doesn't mean that we're just suddenly out of a job. We just hand everything off to the ops team and we're done. It means that, we transition. We're no longer coders, but we're still developers, but we're maybe more builders. We embrace more now that we're engineers. There's a toolbox out there, and we know what the toolbox is. We know what's inside of it, and we learn how to piece things together in a very thoughtful way. And we're really using the same parts of our brain. We're still developing applications, but we're just not writing the code. We're not inside of an editor all day long. And when I say that, I don't mean like it's zero code all the time, because that's not feasible. I just mean that things that we used to write code for are already now services that are very reliable and dependable, and that we can use those instead. And then we move on to something else. And so, for instance, the cloud. The cloud gives us so much more in our toolbox. I mean, every cloud service is essentially like a Lego block that we are, piecing together with other services to create something interesting or to solve a problem. And when we're talking about applications in the cloud and serverless applications, then some of the most basic building blocks might be FAS, or functions as a service. And FAS is code. We write code inside of FAS, but they're meant to be very small microservices or nano services. So we're talking about just, very small snippets of code and not like the giant, Java files that maybe we were used to in the past. And I think too, it's important to remember that cloud services like Microsoft Azure or Amazon AWS or Google GCP, these platform services are so huge. They support customers that are bigger than probably any software system that a lot of us have worked on. And that means that their services, their building blocks are constantly tested on a daily basis. They are hardened, they are battle ready. And so really, you can no longer say, well, I just don't know if I trust this messaging system. I think I'll write my own, because that doesn't make sense. There's going to be, some sort of message bus or something out there that will work for you. You don't need to rewrite Kafka. You don't need to write your own service bus. There's something out there that you can use. And then you can spend that time innovating in a different way. So here's an example of just some things that, at least I personally used to spend a lot of time writing code for that I no longer write code for now, and one huge one is HTTP servers. I just remember every single application I wrote, the first thing was setting up Express or Happy and, setting up all of my routes and setting up my API server. And I just don't have to do that anymore. Really, if I just use API gateway, API management, some services that are, within functions or other fast platforms, I really just kind of click some things in the portal and it's done for me. I don't have to write code anymore. I mentioned before messaging systems, cron jobs, bots. I mean, I'm going to illustrate it a little bit better today during a demo, but, writing bots, I remember just copying over and over again various API calls to create various Twitter bots and Facebook bots and Instagram bots. And, a lot of that now is just really point and click, and it becomes very, very easy. Notification systems. If something happens, then something else. Those are great examples of things that we can do really easily between serverless systems, because notification systems are event-driven. Data parsing, image and video manipulation. A lot of the early serverless examples were, something relating to, editing some video content. And basic AI. I mean, really, if you need a system that looks at a photo of something and identifies it, that exists on nearly every cloud platform now. And those models are trained with a lot more data than the average person would have access to. So here, we're at a serverless conference. This is ServerlessDays virtual, and we have to have the slide of what is serverless. And so, yes, all the things in this slide, but I want to highlight especially event-driven architectures. That's the most important designation here, I think, of what is serverless, what are serverless architectures. But also, since I'm talking about writing less code, I want to talk about, less waste. And I think because serverless systems really lend themselves to this idea of piecing building blocks together, then you do have a lot less waste because you have less code, you have fewer bugs, and things just end up being a lot more streamlined. But, it's important to remember too that serverless is not entirely about FAS. It's not entirely about functions as a service. And that might make you think that serverless is about code because you write code and functions. But they're just simply the building blocks. They are the connectors, connecting one service to another, connecting, APIs, pulling data. They're really maybe even the glue. But they are not entirely what serverless is about. So now I'm going to get a little bit more vendor specific since I do work for Microsoft Azure. And I want to talk about what does serverless look like on Azure. And I think these are kind of the four basic services for event-driven systems on Azure. There are some other things like, static web apps and serverless Kubernetes and even app service as potential building blocks for serverless applications. But I like to highlight these four as the core, with functions being, of course, the building blocks, our fast service, Logic Apps as our workflow tool, which is very drag and drop and user-friendly, like design-friendly, low-code. Event Grid as the event broker, and API management as the system which, manages APIs. With these four building blocks being sort of the center of an application that could use all these other services that I have here. And I'm just sort of illustrating how these are probably going to be the connectors that use other sorts of pieces of this puzzle, with this only being a few of the blocks. And, I'm talking about Azure right here, but obviously on any cloud platform, like this same diagram could be the same on AWS or GCP with just essentially different names. So since we're talking about low code, no code, I'm going to dive a little bit deeper into Logic Apps. And I think Logic Apps is just one of these services within Azure that maybe is not as well known as others. And so I personally really like it. I'm talking about low code, I like to make sure to mention Logic Apps. And it really is a good organizational tool. It's a good integration tool. You can connect functions. You can connect cloud to on-prem. There's a lot of connectors straight out of the box. So you don't have to write that code to connect to Twitter or to Twilio or to Salesforce or to MailChimp. All that is built in. So you're just grabbing a chunk of code that's already tested and tried and true, and you're using it within your application. And that's really, that makes a huge difference. I mean, if you think about how much time you spend just even writing this asynchronous code to grab data from an API and then do something with it, just having that done for you really removes like quite a bit of code. So once again, yes, lots and lots and lots of connectors, 300 plus, some of which are, written by the vendors themselves. So they really have a vested interest in keeping them up to date. And then of course, Microsoft Azure services as well. I mean, you might call it plug and play. I'll just pause here for applause. So this is what the visual designer looks like within Logic Apps. This is just an example here of a common workflow. And each one of these blocks between the arrows is just a different action that's run, with the top action being your trigger. And so a trigger can be really any type of event. It could be a timer, it can be a reoccurring event, it could be an HTTP event. And so there's many, many triggers within the system too, included in the connectors. But of course, if you insist on coding, you want to see code, and I mean, this is very important for your CI/CD pipeline. It does generate JSON here, which is essentially the ARM template that you can use then for DevOps. So now I'm going to do a little bit of a demo, and I'm going to kind of, use some fun, 2020 type related content to create a, very low code application. So yeah, it's 2020. I mean, have we thought about meteor impacts? Because, with everything that's been going on lately, I think it could be a really important topic. So first of all, I want to look at, just show you here, the NASA APIs, if you aren't familiar with. There's some really, really unique APIs here that are just really fun. And, if you want them for demo code, but also if you're just really interested in like some legitimate applications, just using data from space, there's a lot of great APIs here in their library. You can just request an API key. But the one that stood out to me here was the near Earth objects data, which really for a date or a date range, it will tell you how many objects are making their, that are going to be closest to the Earth on that day. And it also will tell you the size, how far away they'll be, and if NASA classifies them as a hazardous asteroid or object, because it could be a comet. So there's also a Swagger UI here for this data. And we're going to be looking today at the Today feed. And I'll just go ahead and run this so we can look at the data. And so it's going to say for today, there are 13 objects in the sky that are objects that are either meteors or comets. And it has a lot of information about each one. But also, like I said, we want to highlight specifically if it's hazardous. And that doesn't necessarily mean that it's still hazardous, but at some point NASA did classify it as so because some of these objects are monitored over the course of decades, and so at some point the trajectory looked like, okay, this could have been a potential hazard to the Earth. And then hopefully, since these are for today, let's hope that if they were still considered hazardous, that we would know about it. So because of that, I decided that I wanted to make maybe a bot that would tweet if there was a hazardous asteroid making, a close trajectory today, or maybe multiple. And of course, us being in tech, anytime anything happens, we need to tweet about it. So let me go to the Azure portal, and I'm going to highlight a couple things. First of all, let me go back to the data here really quick. So one thing I wanted to kind of highlight is that this API, it wasn't structured quite how I needed it to be to easily create some bots. So I wanted to do a little bit of massaging to the data. I wanted to kind of combine this object and this array just to create an array of near-Earth objects, since I'm only grabbing them for one day. And that makes it a little easier to write an open API spec and to work with this data. So first I created a logic app for my data. And I wanted this logic app to be an API itself. It's actually going to pull data from this near-Earth object API, and then it's going to do a little bit of massaging of the data, and then it's going to return a response. But in itself, it is an API. So what I will do is I will then wrap this with an API management service, and then that becomes my new near-Earth object web service. So here, the trigger building block here is an HTTP trigger, and it's a GET. And then here I'm actually calling this web service that I've been referring to here from NASA for today. And then here I'm actually calling an Azure function. And let me move over here to my editor, VS Code, which I love, to show that this is what my Azure function looks like. And I'm choosing to use an Azure function here. I could actually do this data manipulation right within Logic Apps. It could be more blocks. But I kind of figured that might be other data massaging that I might want to do here. This might be something that I really want to be more fully testable. So maybe I want this to be a complete separate piece of code. Maybe this is a piece of code that I want to use for some other type of application separate from Logic Apps. So I chose to put this in an Azure function, but it's still very low code. I only have a few lines in here. And then I also have this open API spec that I created for this near-Earth web service that matches the output from this Azure function. And I'll need that later. So you can see here in API management service that the service is called Killer Asteroids, and then I have these APIs that I can add here. And I want to show here too that even though I've already added this API wrapper for my Logic App response, you can see here where if I wanted to add another one that I could do so from an open API spec, a Swagger spec, a function app, an app service application, a logic app. There's a lot of flexibility here, and there's so much that we could go into for API management. But once again, this is just yet another service where a lot of the functionality that we get out of this API management service would probably be application code that we would have written like even 5 years ago. So now I'm going to go and look at Logic App custom connectors. And I want to mention this because if you can always do an HTTP call within your Logic app to pull data. But the benefit of creating a custom connector, which I'm showing here that I actually built mine using the Swagger file that I showed earlier, this open API spec. But you can also do it from a Postman collection here as well. And basically that just gives a little bit of structure to your data so that the connector knows all the various actions, and also it knows what the request would look like. So in this case, I have a response object here of asteroids. That's all defined within my open API spec. And then within the connector, I'm not just getting straight JSON that I have to then manipulate. It gives me it's a little easier basically to select these different actions. And if you have like really complicated APIs, this becomes really handy. So let's go ahead now and create our bot. So this is a brand new Logic app that is using the data that's a little bit massaged. So the trigger here is a recurrence trigger. I just have it occurring once daily, which is basically all I need since I'm only looking at the asteroids for each day. But of course, each time I just decide to run it, then it's going to run anyway at that moment. And the only reason I have a split here is just for demo purposes to show that this is what the HTTP connector would look like that's hitting my API wrapper. Or I can use my custom connector, which is this asteroids.list. And I have a JSON parser here just so that I can be sure that it's JSON that I'm manipulating. So now I'm going to add a new action here. And what I want to do is I want a control action because I want a for each. And right here it gives me some dynamic content, and it's guessing which thing that I want to loop through just based on what is an array. Now that I'm within this for each, I'm going to add another control, a condition, because like I said before, the thing that I care about most here is whether or not this is considered to be a potentially hazardous asteroid. And I'll say equal to true. Now, of course, if it's true, I'm going to tweet about it. So I'm going to grab this Twitter action to post a tweet. And this is connected to my demo Twitter account, which is called These Cats Tweet. And now here's my text that I'm going to be posting. Huge meteor named, and then I'll grab the name from here. Will be close, but will, scoot over here, not hit the Earth, say today. All right, that looks good. Now we're going to need to save. And we're going to run and see what happens. Okay, well that looks like that ran successfully. And you guys can see it loops through each one of those 13 items. And so then we can look at, and so the first one is true here. I think out of this data set, there's 3 that are true. So let's go over here to this Twitter account, These Cats Tweet. And yes, there were 3 hazardous asteroids for today, and here they are tweeted out of this account. There's also a lot of other demo stuff in this account because I use this for pretty much every talk that I give. But anyway, but yes, so yay! So this is an example of my Logic app working. Now, also quickly, I want to show something else that is actually outside of Azure. And I want to go to Microsoft Power Apps, which is part of our Power Platform. And this is also a low-code, no-code platform outside of Azure that works really closely with Azure. And part of the power of that is using custom connectors, almost identical to what I did in Logic apps. I have a open API spec, and I can use the same one that I used before for my Logic apps connector. And I can look at my Swagger editor here, and this is going to use the same file that we used before, which is here. And the Power Apps applications will be mostly concerned with this asteroids definition down here. Do a quick refresh there. There we go. There we go. And Swagger editor here. And this is basically the same. Now we can look at the definition, and we can see also the same as the custom connector here, where we have some API endpoints that are a little bit more structured. Then this here is my actual Power App that I created using that connector. And so here, if we look at the data, I have this near Earth object connector that I've created a connection to here on the side. And so once this connection is made, I can literally just drag and drop these little components like these labels here. These are all labels, except in this example, if you look up here in the function, I'm calling the element count from that API. It's the exact same function that I was using for Logic apps. And it gives me the same data, which is 13. I also have this data table here, which also is connected to data. And here I'm connected to the near Earth objects array, just like we did also in Logic apps. And when I'm also, let me go back to the data table here. You can see that under properties, we can edit the fields here. And then I can decide which columns I'd like. And I can also add drill downs where I could make a hyperlink here. I could create a whole nother screen, and I could drill down into more data about these asteroids. Because as we know, there's a lot of data about how far away they are, how many lunar distances a meteor might be. So anyway, this is just a really quick demo into a couple services within Azure and outside of Azure to look at some low code, no code scenarios. And of course, these aren't enterprise apps. These are really small pieces. But the idea is that you could piece these together, add these to your toolbox, and make them part of, some sort of enterprise solution. And of course, we want to pay homage to Bruce Willis, who unfortunately did miss a thing. All right, and now I'm going to head over to the Q&A, and thanks a lot for having me.
Hey, all right. Thank you very much for that amazing talk, Linda. And I am joined live by Linda Nichols here. And so I'm watching this talk, and I'm thinking to myself, all right, I'm going to get hit with some Bill and Ted's Excellent Adventure, some Bogus Journey stuff, and then just bam, Armageddon, just plastered with Armageddon references. And a lot. I mean, maybe to the point of being excessive. And I know whenever that's on TV, it's one of those movies where you can't stop watching. Like once it's on, like all right, it's like that and Rudy, and there's a few movies that you just have to keep watching.
Would you say you don't want to miss a thing?
I don't want to miss anything. Exactly. So, all right. So thank you so much for giving that talk. That was excellent. And I love this topic. And you and I actually talked about this quite a bit. You were a guest of mine on Serverless Chats. It was episode number 48. There's a whole hour of us basically, talking a lot about this idea of being a developer. What does that mean now, especially when other people are writing much better code than you could probably write? And that is not meant to be in any way, any way diminishing your abilities. But it's just there's so much code out there. There's so many services. There's so many people who have tested it billions and billions and billions of times. It just seems so much smarter and easier to start stitching these things together, right, than to just build them from scratch. So I do want to talk to you more about Armageddon. But before we get to that, I wanted to ask you, as a developer now, and you said we're sort of turning into builders, is this something where the developer of the future or the builder of the future or the coder of the future, whatever you want to call it, that it's going to be more about IAC, more about infrastructure as code, more about understanding cloud architecture than it's going to be figuring out how to run a for loop?
Yeah, I think so. But I also think that a lot of the IAC is going to fall to the ops team. I think there's still going to be that line in the sand between the development team and the ops team. I think a lot of the DevOps, really DevOps has been all about development. I think a lot of that's going to kind of fall more to ops. We're going to kind of share that handing the ball over that line in the sand is going to be a lot easier. But I think it's going to be just more about design now. I think it's going to be just really about, orchestrating things so that you're creating a super efficient design, and maybe your code doesn't have any part in that. You're just using, everyone else's code essentially pieced together. And it's like, who can do it in a way that makes the most sense? It's the most decoupled. And of course, in serverless event-driven systems, there's automatically going to be decoupled and more efficient. So yeah, that's kind of where I keep going with the builders, and I keep preaching that too, because I'm like, don't lay down your identity on being a coder, or I'm a JavaScript coder, I'm a Java programmer and all that. Like, we're all builders, we're all engineers, and we don't look down on someone that's using low code. Or, we don't also put someone up in an ivory tower because they're so clever to have written something that other people have written a bunch of times already, that already exists.
No, totally agree. So the other thing, though, that I think is interesting about low-code platforms or even no-code platforms is it gives people who are not, your traditional coders the ability to start stitching some things together. And I know you were sort of showing logic apps at the end there, and some of these other things that sort of, it's almost drag and drop. I mean, there's still some code that needs to be done. I think we're going to get past that. But I think it'd be really interesting if you were able to focus more on the user experience. I know that that's something that a lot of developers I don't know if they don't care about it or they just don't want to focus on it, but making that experience better for users and spending more time working on that flow. So do you think, though, that some of these sort of no-code, low-code, services that are out there, is that going to have an effect on developers? Is there going to be less work for developers because we start seeing some of these things?
No, I don't think so. I mean, I've heard this a few times. Like, I was randomly at the car place, and somehow I'm talking to someone telling them I'm in technology, and then someone else shows up, like this, guy who's getting ready to go to college, and he's like, I'm getting ready to go for computer science. My dad said I need to study networking because development is going away. Like, anybody's going to be able to write an app soon. And I was like, okay, but also there are millions and millions of jobs being created every single day for app developers. So if everyone can create one, there's going to be a job for everyone. Right. I don't think it's going to go away. And I still think there's a certain mindset that allows you to write code and write something, or to build something. And maybe you are just dragging and dropping blocks on the screen, or maybe you're designing something more complicated that requires, infrastructure as code. But either way, yeah, it's a certain mindset. And there are some people who just truly enjoy that, and other people who don't, and some people who are sort of better than others. But it's kind of interesting because, with logic apps, you could create a pretty decent API with just drag and drop, no code, And you could think of maybe someone who's more of a designer and like appreciates more of a UI doing that. But then you can also think about, like I showed Power Apps really briefly,
Right.
like someone like me, for example, who's terrible at UIs, like I could create like a really robust backend and then do drag and drop and create this like mobile application and publish it, and it kind of looks like I knew, React or Vue really well or something. So yeah, it's kind of on both sides. I think it's just kind of supporting us. I mean, there's a lot of software to build still.
Right.
There's not a lot of code, specific code, right? But there's still a lot of systems to build and upgrade and modernize. And this is just allowing us to do that a lot faster, and to be more innovative. Give us more time to like do cool stuff and not spend time in the minutia of like another HTTP server.
Yeah, no, I totally agree. Yeah, so that's interesting. I mean, that's the thing too, is that if you think about the majority of even patents today, things that you actually can say, hey, this is something that is unique or is intellectual property. A lot of it has to do with just the patterns or sort of the process, right? So there's still ways to string these things together that can be innovative and unique that people are still going to have to figure out. So that's interesting. All right, one last question. This is the most important question, I think, because I think now that you've watched Armageddon so many times, you can answer this. But the difference between a meteor and an asteroid, what exactly is the difference there?
Yeah, so an asteroid is what the object's called while it's still in space. And once it enters our atmosphere, it's a meteor. So I'm kind of using the terms interchangeably in my talk. And then there's also a comet, and there's also a fireball and other objects. That's why they're called near-Earth objects and not just asteroids. But,
and I believe a meteorite is one that hits the Earth. Is that correct?
Yes.
All right. Perfect.
That's
Perfect.
right.
Well,
Yep. Uh-huh.
All right, so hopefully we answered all your burning questions. Linda, thank you so much for the talk. It was wonderful.
Yeah, no problem.
So listeners, at about 40 minutes past the hour, we have, and I feel so bad, this is a difficult name to pronounce, Rusthem Feyzkhanov. That's why I'm going to say it. Hopefully he will correct me, and we will see him in just a couple of minutes, and we'll be back. Thanks again, Linda.
Great.
Hey everyone, welcome back. Our next speaker is a machine learning engineer at Instrumental. He is giving a talk on serverless for AI applications, and his name is, I'm going to try to pronounce this, is Rusthem Feyzkhanov. Here we go.
Hello, I'm Rusthem Feyzkhanov, machine learning engineer at Instrumental and AWS machine learning hero. And today I want to tell you how to use serverless for AI applications. Let's start by looking at how usual data science process looks like. We start with business understanding and identifying problem and metrics. Then we acquire data which we can use for our model. Then we design our model and train it. Then we deploy our model into production. And finally, we get feedback from the users. But actually, last three steps is a very iterative process. We have to be able to start really fast to get very early feedback from customers. And we need to keep our infrastructure flexible in case we change our model. And finally, we need to be able to integrate our infrastructure into existing infrastructure. When organizing a deep learning application, basically you have to keep in mind three parts of the system. First is data preprocessing, where you need to gather data from multiple sources and prepare it for the model. Training part, where you need to train the model probably at scale. And inference part, where you have to either process it extremely fast if you have real-time requirements, or if you need to being able to process it at scale, sometimes both. Let's start with data preprocessing. First is there are a couple of challenges with that, and first is that you need to gather data from multiple sources, you need to combine multiple frameworks and libraries, and you need to be able to scale your infrastructure. With machine learning and deep learning training, the main issue is that you may need to use GPU instances which are pretty expensive, and you may need to organize complex logic when training your model. And finally, machine learning deep learning inference, where one of the challenges is that you have to be able to support multiple models and being able to process inferences at scale. Here we plan to use serverless approach for deep learning application. So we will use AWS Lambda for short processing, AWS Batch for heavy processing and GPU training jobs, SageMaker for GPU distributed training, and AWS Fargate for long-running processing. And we will use AWS Step Functions to organize workflows, which will unite all these processing units. Let's look at a whole spectrum how we could deploy applications and define what in this case we consider as serverless. Basically, here you can see that like you have something on premise where you control the whole stack, you have functions as a service where you control only functions top of it, you have containers as a service where you control also runtime and container itself. So in our case, I suggest that we use this part of the spectrum, basically between container service, container as a service and functions as a service. And let's start by looking into container as a service and function as a service. Basically, we could consider them to be like serverless cluster, where you don't have to maintain cluster itself. You just want to implement code and launching configuration, and you want service to organize processing for you. It could be something like AWS Lambda, where like one worker is started per job, and you don't have to think about scaling at all. It could be something like AWS Batch, where service maintains its own queue of jobs and just like maintains cluster which it scales based on the queue. Or it could be like AWS Fargate or Amazon SageMaker, where it also it starts one VM per one job. If we look more into differences between these services, we can see that Lambda provides the best scalability, and the best pricing model, as it price happens per 100 milliseconds. But at the same time, it can only be used for CPU jobs, and it has some limits. Batch, on the other hand, has the most flexibility, but at the same time, it's not perfect, and there could be some idle time because it doesn't start one job per one worker or one VM. And there is SageMaker and Fargate, which are poor container as a service, and they have spot instances available, but they have their own limitations. Next, let's look at how CPUs and GPUs could be used for machine learning and deep learning workflows. Basically, there are a couple of parameters which we need to consider when we define whether some of CPUs or GPUs could be used for inference or training. It includes speed, cost, and scalability. Let's compare different instance types and AWS Lambda for inference cost and time. Basically, here we can see the following. As you see, Lambda's inference is the most expensive because it has the most cost per hour for CPU. And you can see that GPU instances, while they have the best cost per one inference, they also are pretty expensive. Two things to keep in mind here. First is inference time, where obviously you want to keep your inference time as low as possible. But even with something like Lambda, you can get it for 300-400 milliseconds, which could be acceptable in your case. And second thing which you have to keep in mind is that even though inferences are cheaper than Lambda ones, keeping one instance up for the whole month costs a lot, and you will need to pay for idle time. And with Lambda, you don't have to do it. So in case, for example, with P2 instance, if you have to pay for the whole month of using it, it's the same as you would have paid for 36 million inferences on AWS Lambda. Now let's compare CPUs based on the cost based on different services. As you can see, AWS Lambda is the most expensive, but at the same time, it provides per 100 milliseconds pricing. And with Fargate and Batch, you have to keep in mind that the minimal time for which you pay is 1 minute. So if your task is significantly less than 1 minute, AWS Lambda is your choice. And if it's a lot more, then you can choose between Fargate or Batch. One of the advantages of Fargate is that you won't get any idle time, and also you are able to customize your instance, depending on whether your task is CPU intensive or RAM intensive. Next, let's compare using different services for GPU. Basically here the main choice is between Amazon SageMaker and AWS Batch. As you can see, SageMaker is more expensive, but at the same time it doesn't have any idle time during training. So it's something which really depends on how your workflow looks like. If you don't have a lot of tasks, then SageMaker is probably better. If you have a steady flow of tasks, then AWS Batch is better. Now let's look at platform as a service, specifically different ways of organizing microservice applications, which we are doing currently. Basically, there is REST API way, event queue, and orchestrator. In this case, REST API and event queue are the cheapest option, and they're different that REST API is the best choice for synchronous applications, event queue is the best choice for synchronous applications. Orchestrator is the best from the perspective that it enables to trace the whole application and handle long-term processes. If we look at cloud-native orchestrators, we get even more advantages. First of all, we get native support for functions as a service and containers as a service. So, for example, with AWS Batch, once a job on AWS Batch is finished, AWS functions can continue the flow. And we also get central monitoring for the whole workflow and central logging and tracing, as well as scaling. If we look at step functions, basically we organize our execution as a graph, and each processing node could be either functions as a service or clusters. And we can organize more complex logic, like error handling, retries, or parallel execution. Now let's look at how we can use all these services to organize specific cases in a deep learning application. First is data pipeline. Basically here we can use modular approach and combine different types of processing units. For example, we can use AWS Batch with heavy CPU processing if we need it. And in case we can parallelize the task, let's say we need to parse data from 1000 websites, then we can launch 1000 lambdas in parallel for short tasks. Basically, how do you know if it works for your case? It works if you have peak loads and you want to scale automatically, and it works if you have some custom logic which you want to implement. Or you need to combine multiple frameworks and have customizable pipeline. Here's the repo which you can check, which has an example deployment for AWS step functions with AWS Lambda, Batch, and Fargate. Next is machine learning deep learning training pipeline. First case is using Amazon SageMaker, where it will handle automatically hyperparameter checking, and it will handle for you model saving and input data. Also, one of the advantages is that it can handle automatic distributed training, so it will start the whole cluster for you and will run distributed training on it, and will stop it once training is complete. Next is using AWS Batch for deep learning training. In this case, you would need to implement handling parameters and data to AWS Batch and saving model from it. One of the advantages is that you, with step functions, you can organize complex logics like feedback loop or test after training. And finally, you can use step functions to organize working with external infrastructure. In case you have on-premise GPU and you want to train your model there, you can use step functions to prepare data for training and trigger the processing on external infrastructure, and then gather the results and publish it into your production infrastructure. In the same repository, you will be able to find example with using step functions with Amazon SageMaker and AWS Batch for GPU. And finally, deep learning inference pipeline. One of the challenges with organizing deep learning inference is that architecture may be a little complex. Basically, you have to define a lot of parts with load balancing, ECS cluster, EC2 instances, autoscaling group, and you also would want to use spot fleet to get the best pricing. If you switch to serverless, infrastructure becomes a lot easier. Basically, it's just AWS Lambda, API Gateway, and Route 53. Or if you want to process batches of inferences, then you can just connect Lambda with SQS. Or you can organize workflow using AWS step functions and connect it to SQS as well. So there could be an advantage with using workflows with AWS Lambda is that you can basically organize using different models, and you can reroute traffic and and organize something like a canary deployment, where you want to route only 10% or some percentage of your traffic through the new model and get the results and compare it with old model. Also, you're able to use different frameworks as well. One of the challenges with using AWS Lambda for inference is how to import model. The usual case is that you have to load model from S3 in case it's pretty large, but there are some cases where you can convert them to TF-Lite or ONNX, and one of the main advantage is that TF-Lite and ONNX require a lot less storage on AWS Lambda, and you may be able to keep models there. Now let's compare inference cost when using AWS Lambda with Inception v3. Basically, here you can see the following. First of all, is that there is a certain challenge with cold invocations where you have to load model from S3, because before you make an inference, you have to load model. At the same time, you are able to keep model in your memory, and during one invocation you don't need to reload it. So one thing you could see is that with 3 GB RAM, where you get 2 vCPUs, you get faster load from S3 and faster inference, but at the same time you may get a more expensive inference. So it's something which you have to keep in mind when deciding how to customize your AWS Lambda. There are a couple life hacks how you can optimize your serverless inference. Most importantly, you have to store your model in memory between invocations. Instead of using S3, you can now switch to AWS Elastic File Storage, which will give you improvement in terms of loading the model. You can store part of the model or the whole model with libraries if possible. And you can also cut your model in different layers and keep it on different lambdas and chain lambdas together. Basically, how do you know if this is for you? If you have a small or pet project or startup and you want to deploy something very early to get some feedback from your customers, or you have very simple model, then this infrastructure can help to reduce cost. Or you have big loads and it will be more suitable because you don't have to maintain large cluster and AWS Lambda can scale very well. How do you know if this is not for you? If you have real-time requirements and you have to provide result under 200 milliseconds, if your model requires a lot of data and AWS Lambda doesn't have sufficient RAM for you, if your model requires a lot of processing power and CPU doesn't work for you as well, or you need to handle extremely large number of requests per month, let's say more than 10 million. At this point, cluster will be more cost effective. There are a couple repositories which you could check, which contains examples of how to deploy deep learning and machine learning libraries to AWS Lambda and Google Cloud Functions. In summary, cloud-native orchestrators are convenient for constructing deep learning workflows and pipelines, and there are multiple services at your disposal which you can use for your deep learning or machine learning applications, and how you use them will depend on your context. And one of the main advantages is you always pay per use, and deploying the services could be pretty easy, so it could even work for research projects. Now let's switch to live demo. So let's start first with deploying example using serverless framework. And now let's have a look at the repo which I have mentioned. Here you can see different examples of how step functions are used with different services like SageMaker, Lambda, Fargate, or Batch. In deep learning training, there is an example of how step functions plus AWS Batch could be used for training deep learning models. Here we can see a configuration file which we are using, where you can define step functions separately, and here you just need to define your ECR name, basically your ECR image name, and that would be it. As an example, we will train a simple model using a fashion-MNIST dataset. As you can see, currently it's deploying the whole stack. So one of the main advantages is that you don't have to deploy anything in advance. You just get this configuration, and you can just run serverless deploy, and it will deploy everything for you in your AWS account. It also has example of Docker image, which is something which you actually need to deploy before deploying configuration using serverless, but it's pretty easy, and basically README has an example how you can use Docker to build image and deploy it to ECR. Okay, as you can see, it just deployed the whole application, and since we connected API gateway with our step functions, we can call step function from HTTP. So now we can see our state machine. And for each job, we can see the whole graph and the current state. Then on AWS Batch, we can see our compute environment, and we can see that the jobs are created. It will take some time for AWS Batch to initialize the cluster for processing. But based on previous examples, one of the advantages is that you will be able to see the logs in CloudWatch for each AWS batch job. Here is the example. As you can see, deployment is very easy, and the whole application is completely pay-as-you-go. So here you only pay for jobs which you run, and you don't pay for anything else. So thank you very much for your time. Here are the links to repositories which I mentioned during my presentation.
Hey everyone, welcome back. I want to thank Rusthem for that excellent talk on serverless and AI. It's something that is really, really interesting to me, and we are joined by Rusthem now. Rusthem, how you doing? Thank you for the talk.
Yeah, I'm good. Thank you. Thank you for having me. It was like good preparing presentation. So yeah. And thank you very much for organizing the conference, because I think like people should definitely know more about serverless.
I totally agree. All right, so I have a couple questions for you, because one of the big questions that, or I guess maybe an objection to serverless, is always about machine learning and whether or not you can do machine learning with serverless. And now with Lambda, we have EFS. We've got some other things. Obviously, if you're using Kubernetes or something, there's different ways that you can do that. But can we use something like Lambda to do deep learning? Is that possible?
I think the answer is like it depends on the context, because basically, and I think it happened in a lot of areas. Serverless didn't conquer them all at the same time. It was like area by area.
Yeah.
And I think in deep learning there are cases where it works extremely well. There are some cases where it doesn't work yet. So I would say cases where like you need to get real-time response, or you need to process maybe tens of millions requests per month, like maybe at like this scale or at this speed you need to have cluster. Mm-hmm. But for the pet project, for POC, small type of project, I think it provides a good combination of pricing and architecture simplicity, which enables people to start really early and show the model to customers really early.
And so speaking about that simplicity, because that's something that, I mean, if you're a data scientist and you're trying to do this massive parallel computing, and you're trying to do all this work, setting up clusters of servers and all this kind of stuff, it's probably outside of your scope of expertise, right? So is this something though that like data scientists can use these pipelines and like just start working on this stuff right away?
I think it's something which, because basically there is always a point like when you have to switch from Jupyter Notebook to something more robust.
Yeah.
And basically at some point you need to solve this case because there is a challenge that you want your experience to be repeatable. So at some point you would need to wrap your environment into Docker. Mm-hmm. And basically as soon as you wrap your environment in Docker, it's actually a very like small distance to run this container in cloud on GPU. Mm-hmm. So and there are a lot of repositories with very easy infrastructure where you can deploy it, and you don't pay like for infrastructure itself. You still only pay when some instance is started. Because ideally, all data scientists want the same way. They just want to start GPU instance, run their experiment, and then close GPU instance.
Yeah. Yeah. Well, I know. So I'm not a machine learning expert in any way, shape, or form, but I do know that certain algorithms work better with the GPU or with a CPU and so forth. Is this something where like what does serverless give us the ability, or maybe it's the cloud and Fargate and some of these other things? Does it give us the ability to kind of mix and match CPU and GPU and run these things in parallel? Like, is that a benefit to being able to kind of switch the different, I guess, workloads, in parallel and run that to do some sort of machine learning process?
Yes, I think there is definitely it's a good way to optimize a lot of workflows, because usually you want to use your GPU only for training deep learning model. But usually, if you look at the high-level process of training the model, you have a lot of data pre-processing, you have a lot of testing afterwards, for which you don't need GPU. And if you put all this workflow inside GPU instance, then basically you have idle GPU. So although you run CPU, but GPU is idle. And separating these workflows is a way to kind of decrease GPU idle time, I would say.
Awesome. All right. Well, I'm going to have to watch your talk like 8 more times until I fully understand it. But I appreciate it. I know the listeners appreciate it. Thanks again, Rusthem. It was a great talk. Thank you.
Thank you very much.
All right, so listeners, so we are going to take a 15-minute break. We will be back at 25 past the hour with Rich Buggy and his talk on building single table designs in DynamoDB with AppSync, which should be a great talk. Also, make sure you go to the Discord channel. It's discord.serverlessdays.io. You can log on there, ask some questions, and we'll try to get them answered in these Q&A. So we'll be back very soon. Thanks again, and Rusthem, we'll talk to you soon. Thank you.
Thank you.
Hey everyone, welcome back. I hope you had a chance to get a cup of coffee or a drink and refresh yourself. We have 3 more amazing talks to go. And the next one is from the head of technology at Bailey Nelson. And this is all about single table DynamoDB designs and actually connecting to those using AppSync, which there's been a lot of debate about whether or not you could actually do that. And the answer is yes, you can. And so here is Rich Buggy, and he's going to tell you exactly how you can do single table DynamoDB for AppSync.
Welcome to Single Table DynamoDB for AWS AppSync. My name is Rich Buggy, and I am the head of technology at Bailey Nelson. We're an optical retailer with stores in 4 countries around the world. I have over 25 years experience in software development and started working with AWS in 2009 and Lambda in 2016. I'm also an open source software contributor and maintainer of the AWS SAM Webpack plugin, and I blog at goingserverless.com. So the agenda for today. I'm going to start by quickly explaining what AppSync is, what DynamoDB is, multiple table versus single table DynamoDB design, and then the bulk of this talk is going to be covering how to implement common AppSync access patterns with a single DynamoDB table. So what is AppSync? So AppSync is an AWS service that provides a serverless GraphQL API. It supports queries, which allow you to request data from the API, mutations that allow you to update data in the API, subscriptions that allow you to receive notifications when data has been updated. AWS sometimes refers to this as real-time in their documentation. It will also handle authentication for you, and you can directly access a number of data sources, including DynamoDB, Elasticsearch, other API endpoints, Lambda, and RDS. It's also commonly but incorrectly used interchangeably with Amplify, which is another product from the same team. So what is DynamoDB? DynamoDB is a key value data store. It's schemaless, which means that you can store any type of data in the table. There's no relationship between the objects, and there's no joins when querying. So when you write data, you're optimizing for read rather than write, which means that you'll frequently end up denormalizing data. And when it comes to billing, you have a choice between reserved capacity, where you pay for provision throughput, or on demand, where you pay per request. If you're just starting out with it, go with on demand. So multiple table DynamoDB. So with multiple table DynamoDB, each table stores the data for one GraphQL type. So this is kind of putting a relational database model onto DynamoDB, except that with a relational database, you do actually have that restriction that each table can only store one type. With DynamoDB, you don't. If you need to store additional data, for example, connections or other metadata, then you're going to need additional tables to do that. The GSIs, the global secondary indexes on a table, use attributes that are specific to the GraphQL type. And it's frequently claimed to be easier to implement because it requires less upfront design work, although I'm hoping that I can show you that that's actually not true. So single table DynamoDB. So with single table DynamoDB, you have one table that stores all the data and all the connections, everything for your API. To do this, you need to use a generic primary key so that you don't need to have a common ID field across all of the types. And you need to use generic global secondary indexes that can be reused for different types. So let's talk about some of the common access patterns. Now, before we do this, I've made some assumptions to make the demo easy. The first one is that every type will have an ID attribute that identifies the record, And the second one is that the ID is globally unique. If that's not true for you, I do have a blog post where I explain some other options that might help you. So the primary key for the table. The primary key for our table is going to be an attribute called PK. In PK, we're going to store the ID for the record prefixed with node hash. Now I'm adding that node and hash at the start of it in order to create a namespace so that I can store other data in there. That's also the reason why I'm not using the ID attribute itself to store as the primary key. There's also going to be some data attributes related to the GraphQL type. So almost every GraphQL type is going to have a type name and an ID, but it may have other attributes as well. So let's look at a simple example. So I've got a farm, and the farm has an ID and a name. And in order to create a farm, I have a create farm mutation that takes in a name and returns an ID. So in my DynamoDB, what I want that to look like is this. I'm going to have a PK attribute with node and the ID for the record. I'm going to have a type name of farm. I'm going to have an ID, which is the ID that will automatically be created for it. And I'm going to have the name Old McDonald's, which is the name of the farm that we're creating. So in order to do this without exposing my implementation, particularly around using PK as the actual primary key for the table, what I need to do is I need to do a little bit of work inside my resolvers. So inside my request resolver for create farm, what I need to do is at the top of it, I need to generate an ID, and I need to put that into the input, and I need to put the type name into the input. And then when I go to write the data into the database, what I need to do is I need to tell it to use the PK attribute instead, and I need to map the ID into there correctly so that it's node hash and then the ID for the type. So what that gives me is my record looking like this. When I go to retrieve this record, again, I don't want to expose the fact that there's this PK thing. I just want my users to see this as an ID. So when they call the getFarm query, they're going to pass in an ID and they're going to request a name. What my resolver will do is it will take the ID from the args and it will prefix that with node hash, and then it will look in the PK attribute for me. Another common pattern is unique secondary indexes. So, and a good example of this would be an email address on a user record where we want the email address to be unique within our system. In this case, I'm going to make the farm name unique. So in order to do that, I'm already writing some data into DynamoDB. I'm writing my node with my type name and my ID and my name. But DynamoDB doesn't allow me to just go, please make the name attribute unique. The only attribute that I can make unique in DynamoDB is in fact the PK attribute, the primary key. So what I need to do is I need to actually write two records into DynamoDB. The second record is going to have a PK consisting of the type name, the name of the field that I want to make unique, and the value of that field. What I can then do is I can use transaction write items to write both those records at the same time and guarantee that either both of them or none of them are written. And when I do this, the first record that I'm going to write is going to have that node hash ID PK value, and it's going to have a condition that that doesn't exist. So this stops it from writing a duplicate record with the same ID. And I'm also going to write one that has the PK farm name and then a lowercase version of the farm name. And I'm doing that so that you can't get around my rule by putting in a slightly different case of the name. And I'm going to put a similar condition on that saying that it can't exist. So what happens now is when you do a create, it actually writes 2 records instead of 1 record, but it also guarantees that the name is unique, because if you try to put in the name that already exists, it's going to fail on one of those records and the whole transaction will roll back. Now, having this extra record in here, the one with the farm name and then the value, allows me to also look up the farm by the name. So I could have a query like this that does get farm by name, passes in the name, and it can reconstruct that key and then do a get item to get that farm back. Now, it might not be particularly useful with a farm, but if you have something that like has a barcode or a product code or ISSN, ISBN, email address, something like that, where you've sort of got this natural key, it can be good to be able to have something that's stored against a unique ID that's generated inside your application, but is also accessible very quickly by that natural key. All right, so let's talk about one-to-one relationships. So in the one-to-one relationship, our farm is now going to have an image. And we can see here that the image is accessible from the farm by looking at the image field. So the query to get that might look something like this. I'll get the farm with ID 1. I'm going to request the name and the ID and the image. And for the image, I'm going to request the URL. So how do we implement this? Well, the first thing is we're going to have a create image mutation, which I'm not going to cover here, but it basically just creates an image record. We're then going to modify our farm record, our create farm, so that our create farm also takes in an image ID. And then we're going to store that inside our DynamoDB. So what we end up with is there's the image that would have been created from the create image, and then there's the farm with the image ID now stored against it. So how do we implement the image resolver? And it turns out that it's just a get item. In fact, what I do when I do a get item is, remember the farm has that image ID stored in there. So what I can do is I can do a get item for node hash and then the image ID. Now to get the image ID, that's available inside the context in a source attribute. And what the source attribute contains, because this is the image field being resolved on the farm type, the source attribute will contain this record here. So that's how you get the image ID for it. So what about many-to-one relationships? So let's start introducing some animals onto our farm. So our farm now has cows, and cows have an ID and a name, and they belong to a farm. And we have a farm which has an ID and a name, and it has potentially many cows. So what's this going to look like in terms of a query? So if I'd have a query, I'm going to get a cow by an ID, or I could potentially get lots of cows. And then I'm going to query the name of the cow and the farm and the ID for the farm and the name for the farm. So inside DynamoDB, what I'm going to do is I'm going to add some extra cows in here. So I've added a cow called Bessie and a cow called Daisy. And they have the type name as cow and the ID and the name, and they have a farm ID in there as well. And the farm ID is how I'm going to go and do this. So when I'm on the cow and I need to go and query the farm, what I can do is I can look at the farm ID, and I know that the primary key for the farm is going to be node hash and then that farm ID that's stored on the cow record. So I can now quickly look up the farm using a simple get item. So what about one-to-many relationships? What about the opposite direction? What if I'm going from the farm to the cows? So a query here might be, I'm going to get the farm by ID, and I'm going to get back the name, and I'm going to get the cows on there, and for each of the cows I want to get the ID and the name. Well, this is a little trickier, and this is where I'm going to have to start to introduce some of my generic global secondary indexes. So we're going to start with the fact that we've got our regular old attributes that we know about already. We've got the primary key, we've got all the attributes for the types. But what I've introduced now is a global secondary index, and this is a generic one called GS01. It has a partition key, PK01, and it has a sort key, SK01. So every time I need to add a new key, I just call the next one 2, 3, 4, and so forth. Now, when I write my cow record, I need to write these extra attributes. And it turns out they're actually quite formulaic. So for PK01, what I'm writing is the type name, hash, and then the farm ID. That's why both Bessie and Daisy have the same value in PK01. In SK01, I'm writing the value that I want it to be sorted by when we're coming from the farm to the cows. Now in this case, what I've done is copied across the name. And some of you might be thinking, hang on, you're duplicating data here. This is really bad. But it's actually not. This is actually one of the areas where I think the single table solution has an advantage over the multiple table solution. With the multiple table solution, what people are likely to do is to put a partition key on the farm ID and a sort key on the name. And yes, you're not duplicating data, but now you're sorting things according to the way the name was entered. So if you have somebody entering some cow names all lowercase and some people entering them, all uppercase, and some people entering a mixture of cases, you end up with this sorting that's a little bit odd and weird. Whereas the way it's done here, because I'm writing the lowercase value of the name into SK01, it's always going to be sorted alphabetically, but when the user goes to actually look at the name, they're going to see the name attribute as it was originally recorded. So when we're coming from the farm to the cows, our source inside the context has the farm record. So our source has the ID, for the farm ID is 1. So what we can do is I can now do a query against GS01, and I'm going to do a query for where PK01 is equal to, and then I'm going to pick up cow, because I know that the type I'm trying to return is a cow, and from source I can just get the ID because it's the farm object, so the farm object stores its ID as ID, and what that will give me back is my 2 cows. Now, I've said so far that you can write things. I could use lowercase names in order to give a case-insensitive sort, but you can also do other things too. You can group. So, for example, here what I've done is if the cow has been sold, when I write the name into SK01, I prefix it with an uppercase S, and if it's available for sale, I prefix it with an uppercase A. So now when I follow that same connection from the farm to the cows, what it's going to do is it's going to group all the cows that are available for sale first, and then all the cows that have already been sold, and within each of those 2 groups, it will sort them within name. Now, you can do something similar with what they call sparse indexes. Now, sparse indexes, what I can do is I can conditionally write attributes. So what I can do is I've written PK01 and SK01 always, so you can always go from the farm and get a list of all the cows at the farm. But what I've done here is in PK02, I've only written the record when sold is false. So if I was to do a query against PK02, I wouldn't see the cows that have been sold because they're not in that index. All right, so let's talk about a much more complex example just to show you how this whole thing can work together. So what I've got is I've got my data for my types. I've got the farm, I've got cows, I've added some sheep, ducks, sheds. I've added in IDs for all of these. So let's look at PK01. So this is my first global secondary index. And the first thing you'll notice is that I've written different things for different types. So for example, for a farm, I've written the word farm, and then I've written the name of the farm in as SK01. So what this would allow me to do is I could now search PK0, I could search the GS01 index for a PK01 equal to farm, and it's going to return all of my farms to me in alphabetical order. Similarly, I could search for all the cows that belong to a particular farm, all the sheep, all the ducks, or all the sheds on a particular farm, and they're going to be returned to me in alphabetical order. Now, it turns out that cows and sheep and ducks are all animals, and in my schema, they might all implement the animal interface. And I might want an easy way to go from the farm to just any of the animals on the farm. So what I can do here is I can use another index. So in this case, GS02, and I'm going to use in PK02, I'm going to write animal, which is the name of the interface, and then the farm ID. So again, it's very formulaic, and I know that for every cow and sheep and duck and everything else, I need to write those in there. And I'm going to write a lowercase version of the name in there. So I can now use this index to go from the farm to the animal, and it will return all of the animals. Now, you don't have to just store a connection from one type to another in there, like one specific type to another in there. So in this case here, what I've done is I've stored in SK03, I've stored links between the shed that an animal is in and the animal itself. So I can tell, for example, all the cows that are in a particular shed. Now, sorry, before I go on, when it comes to how many global secondary indexes you're going to need, the number doesn't actually grow as badly as what you might think, because we are actually reusing indexes. It actually turns out that the number of indexes that you require is determined by the type with the maximum number of connections back into it. So what I mean by that is, if you take something like a cow, I've got a connection between the farm and the cow is one. There's the farm and the cow as an animal is one. There's one between the shed and the cow is one. So I've got 3 global secondary indexes there to use. And providing I don't have another type that needs more than 3 global secondary indexes, I can just keep reusing these ones without needing to add more. So what this means is that the growth in global secondary indexes on your table actually slows down after a while, and you might find that you can go many months, even years, without actually needing to add additional secondary indexes. You also tend to find that you don't need as many secondary indexes as what you think. So I've had schemas with 25 types, and they've only required 6 GSIs. Okay, so let's talk about many-to-many relationships before I finish up. So a many-to-many relationship. So here I'm going to switch over to using a property example. So you have a property which can be owned by many people, and you have a person who can own many properties. And in a relational database, this is fairly easy to model. You've got a join table, and you can quite efficiently join from one to the other. It doesn't work so well with DynamoDB. So there's been a lot of encouragement of people to go and create intermediate objects in between them. So what we might do is we might have a person owns, and then they have an owner record, and the owner record says this is the person and this is the property, and then the property has owned by, and then it has many owned by records, which again, it's the owner record with the person and the property. Now, when it comes to querying that, what your query will look like is something like this. So you'll list all the people, and then you'll get their ID and their name, and you're going to go to the owns, and then you're going to query the property that they own, and you're going to get the ID and the address for the property they own. There's a little problem with this though, and if you don't actually understand what the underlying queries are doing here, you might get tripped up by this. The problem is that when I run list people, this might be a really efficient query and it might return 1,000 records. So then we get down to the owns, and the owns now has 1,000 queries that it needs to run. And if it turns out that the average person owns 3 properties, then when I get down to the property, I've got to run 3,000 get items, which means to run this query, I've now got to run 4,000 DynamoDB operations. Now that's a little insane, and that's going to be really bad for performance. So what you want to do is you want to look at alternatives to this. There are things like adjacency list patterns that you can implement. You can also just denormalize the database is one way of validly doing this. So maybe what you do is, instead of having the owns, maybe what you do is you sort of copy the property and the owns data together into a separate table. Sorry, not a separate table, into a separate attribute. So the last thing I want to cover here is just schema migrations. So when you do a schema migration in a multi-table, you're going to end up doing a mixture of updating DynamoDB GSIs, which can only be done one at a time, and updating data. And this is one of the reasons why I don't like the multiple table solution, because if I do need to go and update GSI, then I may end up needing to run a migration multiple times in order to get this to happen. If you're doing a schema migration with a single table, it's mostly going to be updating data because of the GSI reuse. You're less likely to need to actually create a new GSI or to modify a GSI. Now, there are some hacks that can help you with updating the data, including forcing clients to deal with missing data, so null values, and using resolver templates to add missing data. So questions?
Hey everyone, welcome back. I am here with Rich Buggy. Rich, thank you so much for that talk. I love this topic. I said that before the talk started. Question for you. You talk about single table, right? And we've had a lot, Rick Houlihan talks, all this kind of stuff. And if people aren't familiar with DynamoDB and they're not familiar with Rick Houlihan, go and watch his videos. They're absolutely amazing. I think it'll blow your mind. But I'd love to get your perspective. Why you mentioned sort of single table versus multiple tables, but why single table?
Yeah, so when I started using AppSync, there wasn't really the option to use a multiple table. So you could use multiple tables, but DynamoDB itself, for its pricing, you only had the reserved capacity. Now, if you've got reserved capacity on a single table, it's only going to cost you a little bit of money. But if you've got reserved capacity on 40 tables, suddenly it starts to get really expensive really quickly. So that's sort of what sent me down the path of, how can I do this with a single table instead of having to have lots of tables? And then, yeah, it sort of spiraled out from there. And I ended up sort of where I am now, sort of really strongly advocating, single table is just, it's a lot easier to use in terms of just managing it, in terms of data migrations.
All right. So we have a question from the forum, and it is, while working with AppSync and DynamoDB, do you have any recommendations on how to maintain or debug the VTL templates? Are there any good observability tools to trace requests through to your resolvers?
Right. So what I usually end up doing actually is when I'm developing stuff, I tend to actually develop using, believe it or not, actually the AppSync console. I've actually found that's the fastest way to do things, because you can make changes to your templates and you can do a test really quickly to see what's going on. In terms of testing it in production, probably your best option is to turn on logging and just sort of look at your logs to see what's going on. They do actually produce quite good logs about what's going on, what the request is evaluating to. I have actually started working, though, on a side project to do exactly this, because it is sort of a problem area for people who are doing a lot of VTL.
All right, so I got another question here, and this person asks, they said that they've been doing single table DynamoDBs for quite some time, but have you had any difficulties where when you want to add additional features or make changes in functions that you have to make big changes to your table designs?
We haven't had to do that. So one of the advantages of sort of having the generic indexes is that you don't sort of have to do that so much. When you do have to make changes, you can sort of mask them in VTL. So I guess one example we had at one point was we changed the way images were stored, and we actually turned images into their own separate object. Previously, they were sort of embedded into another object, and we were able to sort of hide that underlying change because of the way the VTL worked and because of the way the resolvers work. So previously, what would happen is that the resolver for the main object would just grab the attributes for the image, and then when we sort of made this change, well, the new resolver would then go off and grab the new image object itself. So yeah, I tend to sort of find that AppSync sort of hides some of this stuff.
Mm-hmm.
Yep.
Yeah. Nice. All right. So one last question here, and this was asked a little bit earlier. I know you were addressing this in the chat, but just for everyone who's listening. So the question was about using generic GSIs versus named GSIs. So when you're building a single table design, obviously you only have so many GSIs available. So what are your thoughts on using sparse indexes and named GSIs versus the generic GSIs?
Yeah, so I actually use both of those, which we sort of saw in my examples there. So I always use generic GSIs. I do this because I don't want to run out of indexes. The only time I have ever considered using a named index was actually on the type name, because virtually every record has a type name. I also tend to use the sparse indexes as well. So the example there being I might or might not write data into an index depending on whether I want the record to show when I run a particular query. So bit of both.
Sense.
Yeah.
Right. Yeah. And then you also have that limit too, if you start doing projections, how many total projections you can have. And there's a lot of things you've got to, when you start using multiple indexes, it gets a little bit confusing. So, all right. Yeah. Well, Rich, thank you again for the talk. It was great. For our listeners, we have Will Velida coming up in just a couple of minutes. So we're going to take a short break and we will be right back with his talk. Thanks again, Rich.
Okay. Bye.
Hey everyone, welcome back. Our next speaker is a software engineer at ASB Bank in New Zealand. Will Velida is going to talk about building event-driven applications using Azure Cosmos DB and Azure Functions. Will, take it away.
Awesome, thank you very much. Let me just share my screen. And welcome everyone. Thank you so much for joining me today. Good morning, good evening, wherever you are in the world right now. I hope that you're healthy and safe. Thank you so much for joining me. My name is Will Velida. I'm a software engineer and Microsoft Data Platform MVP based in Auckland, New Zealand. Just sharing my screen. Awesome. I think that's working now. Cool. Now, I'm really excited to be able to talk to you all today about building event-driven applications using Azure Cosmos DB and Azure Functions. Now, when I do these talks in real life, I usually go around the room and take the opportunity to ask people whether they've used Azure Functions or Azure Cosmos DB, just to see what their experiences are with using both of those two technologies, if they've ever used them before, if they're using them in production, whatever, just so I can set expectations for the session. But since I can't actually see all of you all today, this session doesn't require you to be an expert in anything I present today. You might be considering using Azure Functions or Cosmos DB or a combination of both. You might have deep experience using both of them, either in isolation or together, or you may have no experience whatsoever. You may not even have heard of them before. So today is all about me just showing you how you can use Azure Cosmos DB and Azure Functions together to build some really interesting and event-driven applications. Now, I will be doing a little bit of a demo today, and I'm fairly confident about my chances. The code demos will be in C#, so if you do have a bit of C# knowledge, that's great. If you don't, don't worry about that. It doesn't matter. I'm sure you'll be able to follow along, and I'll explain it as we go along. Cool. So today I'll just start off by giving everyone an overview of what Azure Cosmos DB is and what we can use it for. And then I'll dive into the details on how we can use Azure Functions to work with our data in Azure Cosmos DB via the different Azure Function bindings available to us. Then I'll talk a little bit about dependency injection, how we can use that in Azure Functions to work with Cosmos DB clients, and why we might take that route over using Azure Function bindings. And then I'll go through a demo. So I'll show you how you can use dependency injections within your function applications to instantiate your Cosmos DB clients, so you can share across multiple functions within a function applications. Dive into any questions that you guys might have. Sweet. So let's dive into it. So Azure Cosmos DB is Microsoft's globally distributed multi-model database service. So using Cosmos DB, we can build databases using a variety of different data models. So we can build applications that use document models, either using the SQL or MongoDB API. We can build applications using columnar data, using the Cassandra API. Key value data using the table API. If anyone here has had any experience using Azure Table Storage, essentially Cosmos DB provides a table API that allows us to build globally distributed applications using table storage. Or perhaps you're working with graph data and we can use the Gremlin API to build applications that interact with graph data. And Cosmos DB provides us with the ability to build highly responsive and available applications worldwide, ensuring that our data that we use in our applications is as close to our users wherever they are in the world. The benefits that come with Cosmos DB, there's turnkey global distribution. So that means Cosmos DB will replicate your data to wherever your users are. It's a foundational service in Microsoft Azure. So you can add or remove any Azure region in the world to your Cosmos DB account, and Cosmos DB will actually replicate your data to all regions that are associated with your account with zero downtime. Cosmos DB provides elastic scalability for both throughput and storage worldwide. So you can scale. This is really great if you need to scale up from serving thousands of requests to millions of requests per second, and then you only pay for the throughput that you provision to help deal with the traffic workload that's put onto your database. There's guaranteed low latency at the 99th percentile. So this helps us build highly responsive planet scale applications, and Cosmos DB comes with guarantees of less than 10 millisecond latencies for both index reads and writes at the 99th percentile, which is really great for providing rapid queries and responsive applications. There's precisely defined multiple consistency choices. So with distributed databases, you're usually stuck between eventual and strong consistency. Cosmos actually provides us with 5 well-defined levels of consistency, depending on the needs of our application requirements. And also there's no schema or index management. So Cosmos DB automatically indexes all data and is schema agnostic, meaning that we don't have to worry too much about these when developing our applications. We don't have to deal with any downtimes that we might have to deal with when changing indexes. There are some caveats with that, but out of the box, you do get automatic indexing of your data and you don't have to worry about your schema. And we can use Cosmos DB in a variety of different use cases. So in my demo today, I'm going to show a very basic IoT telemetry demo. So essentially, we might have IoT devices all around the world, and we need to read recordings and from those devices. Another example that we might have is we might have a mobile game that's used by gamers all across the world, and we need to be able to replicate the data to them in a region as close to them as possible for rapid performance. We can use it for web applications, retail and e-commerce applications to provide customers with ultra-fast retail shopping experiences. Essentially, if we need a NoSQL database service that's ultra-fast, doesn't require a lot of management from our part, then Cosmos DB is a fantastic choice for our data requirements. And Azure Functions works really, really well with Azure Cosmos DB. So for those of you who may not be too familiar with Azure Functions, Azure Functions provides us with the ability to create scalable units of work or precise pieces of logic that can be run on demand without provisioning or any managing infrastructure. And by using Azure Functions with Cosmos DB, we don't have to create this full-blown monolithic application we don't need to develop this monolithic application to interact with a database. We can create small reusable functions for specific tasks that allows us instant access to our data. And we can work with schemaless data as well, so we don't have to worry about, we can build small units of work that can handle any type of data outputs. They can scale, they're pretty scalable as well, so throughput can be scaled up and down in Azure Cosmos DB. So if you have thousands or hundreds of functions querying and writing to the same container, you can scale up your throughput that you provision on the Cosmos DB side, and you can work with many different functions in parallel. So we can build event-driven applications that scale globally as well. So thanks to Cosmos DB's ability to replicate data to different regions across the world, we can develop provision applications, event-driven Azure Functions that interact with instances of our Cosmos DB accounts that are closest to our users. And Azure Functions are event-driven as well, so we can use this to listen to change feeds from Cosmos DB, which I'll talk a little bit about later and also show you a demo on. So it means we don't have to create this really sophisticated listening logic on our database. We can just provision an Azure, create a small Azure function really easily and really quickly to monitor and listen to changes on our Cosmos DB database, Functions is a really good way of actually spinning up something really, really simple and brilliant for really executing some really quick and efficient tasks. Now, there are different ways we can use Azure Functions to interact with our Cosmos DB databases. So we might want to execute a function that whenever a document is created or modified within a collection in Cosmos DB, we might want to create an Azure function that uses a Cosmos DB trigger to listen to those changes happening inside our container and then perform another action. We might want to do a very, very quick read in our collections based off a SQL query, and we could use an input binding for this. Or we might want to write out some data to a Cosmos DB collection. Say we've got a function that's been triggered by Event Hub or an HTTP request. We can use an output binding to write some data really, really quickly to Azure Cosmos DB. So let's go through some visual examples of this. So first we'll start with the change feed. We can enable this using a Cosmos DB trigger. And this is a really, really simple way of using the change feed inside Azure Cosmos DB. So essentially what we're doing here is we'll set up our function with a Cosmos DB trigger to listen to a container that we specify within our trigger. And then every time a document is created or updated inside that trigger, our function will be invoked, and we can produce an output based on those changes that have happened inside our trigger. And I really want to just go into a little bit more detail about what the change feed is. So say we have a function here called purchase product. Say we have an e-commerce site, and every time a customer creates an order, we can use the change feed to produce an output depending on what we might want to do with that order that our customer has created. So for example, we could use the change feed to persist our document to another collection in Cosmos DB that might have a different partition key. We might be executing we might have our original product collection here that's optimized heavily for writes, and we might want to use the change feed to then take that document and then place it into another Cosmos DB collection that we've optimized for read-heavy situations. That might be something that we want to do. We may want to take our JSON document and do a bit of archiving on it and store it in a colder storage that might be more suitable for analytical workloads. And we also might want to use the change feed to do some sophisticated intelligence on the orders that our customers have made. So for those of you that may be more familiar with, Azure Databricks, we can use the change feed. An example here is we can use the change feed connector for Spark, listen to changes, listen to documents that are being created or updated inside our container, use the change feed to then send that to Databricks, and then perform some machine learning jobs based off changes in our collection. And essentially, any changes that occur within our container are processed as a sorted list of documents in the changes that which changed in machine. For the Databricks job. So we aren't limited to just a single producer. All of these consumers can consume the same change feed to do some parallel processing. Now, in terms of setting up the Cosmos DB change feed, it's enabled by default on all Cosmos DB accounts. So all we have to do is set up our function, and then we can start processing changes in our Cosmos DB containers immediately. Functions aren't the only can work with the change feed. They also provide a processor library. You can also use the SQL API. There are different ways of interacting with the change feed, but that's kind of out of scope for this talk. That's just a real simple introduction, real one-on-one introduction onto using the change feed in Cosmos DB via Azure Functions. And there are also there's also input bindings as well. So we can use input bindings to read data from our Cosmos DB collections through an Azure function. So say, for example, we have an HTTP trigger that's part of a serverless API that we've created, and we want to perform a particular query that retrieves data from our collections in Cosmos DB, or a collection, sorry, in Azure Cosmos DB, and then we can use that to output to return documents to the user as part of a web page. Essentially, for input bindings, if we need a subset of our data in a Cosmos DB collection, we can use an input binding to execute some really simple and really easy queries to get that data back to us. And there are also output bindings as well. So we would use an output binding to then write data back into our containers in Azure Cosmos DB. So as part of that serverless API, we might have an HTTP trigger making a post request as part of that API, or we might be reading events off an event hub that we want to consume and then persist into Azure Cosmos DB. We can set up a really simple Azure function with a Cosmos DB output binding to write data to our containers. And using bindings is a really, really simple way and a really, really quick way to start creating Azure functions that interact with our Cosmos DB database. That's really, really quick and really easy to do. However, there are some limitations with using bindings. Currently, the bindings only support the SQL API in Azure Cosmos DB. So like I said at the start, there are 5 APIs for us to choose from when we're provisioning our Cosmos DB account. But if we're interacting with a Cosmos DB account that wasn't using the SQL API, and we wanted to use Azure Functions to interact with that data sitting within that Cosmos DB account, we would have to use static clients or dependency injection. With bindings, every time it's invoked, it instantiates its own client. So if we have one function that executes every so often, this isn't a massive problem. Say if it executes once every month or once every week, it's not such a big problem in terms of performance. However, if we have multiple functions within a function application trying to interact with our Cosmos database, this will cause a little bit of a performance hit. And depending on how you actually host your Azure functions, there's also that to consider as well. So it's really easy and really quick to get set up with Azure Functions with Cosmos DB. But depending on how many functions you're provisioning, depending on how many times you're interacting with your Cosmos DB database, depending on what hosting plan you're hosting your Azure Functions on, there are some performance issues to consider as well. And the bindings themselves, so the Cosmos DB.NET SDK, this is for C# developers, they still use version 2 of the .NET SDK for Cosmos DB, the bindings in Azure Functions. Version 3 has been out for a while now, and there have been some massive improvements in performance and ease of use for the SDK. So if you're in a position where you can use the latest and greatest version of the SDK, then bindings are probably not the way to go. However, from version 2 of the Azure Functions runtime, Azure Functions supports dependency injection. They're built on .NET Core dependency injection features, and they have the same lifetime, same service lifetime, as ASP.NET dependency injection. So if you're familiar with that, so we can create transient lifetimes, scoped lifetimes, which matches the function execution lifetime, or we can create singletons. So we can create a singleton object of our Cosmos DB client, and then have a bunch of function apps that actually share that singleton instance of our Cosmos DB client. Cool, so let me jump into a demo gracefully. Cool. All right. So here, I hope people can see the screen. If not, do shout out. So here I've got a function application that essentially what we're doing for this demo example, we're going to, like I said, we've got a bunch of devices all around the world, and we're going to be taking some device readings off them. And we're going to be sending these readings to an event hub. And this event hub is then, we're going to have another function that listens to this event hub trigger, and then takes the events that are processed through our Azure Event Hub and persist it to Cosmos DB. Then we're going to have a Cosmos DB trigger function, which is essentially the change feed that's going to listen to updates inside our container. And then persist it to another container that is more suitable and more optimized for read-heavy situations. So here I've got my class for a device reading. So it's just very simple properties. We've got a device ID, the temperature that we're recording. Maybe we want to see what kind of condition our IoT device is in. So we want to see what damage level has occurred to the device itself. We want to see how old the device is. So say if we have a high turnover, if we're just using cheap devices, we want to see how long it's been out in the field or how long it's been in its location. And then I'm just going to have a location for this device as well. Before we jump into the functions, I've got my startup class here. So essentially, I'm registering the services that I'm going to be using and configuring and adding this to my functions host builder. So here I'm adding a little bit of logging. I'm setting up my configurations. This is just a local settings.json file. So I've got all my environment variables, so my keys to my Cosmos DB account, the names of my containers, my databases, also my connection strings to the event hub. I'm just putting that in a settings file. And then down here, I'm adding a singleton service of my Cosmos DB client, passing through some Cosmos DB client options as well. And I'm also adding a singleton to my event hub as well, event hub client as well. So my first device, to actually order to trigger and generate some events, what I'm going to do here, I'm using Bogus here just to create some fake data. So I'm just going to create about 100 events to generate some random device recordings. So I've got my device temperature from 0 to 150 degrees or Celsius, Fahrenheit. I didn't really, I work in Celsius, so apologize if that seems really hot or cold to you. I'm not sure either or. I've got a damage level, so low, medium, or high. Device age in days between 1 and 120. And then I'm just going to pick from a random bunch of regions to set as my location. I'm going to generate these fake events just on a GET request. I'm just going to trigger through Postman. And then for each reading, I'm going to send this off to Event Hub. And then I've got this function here that will listen to that Event Hub, connect to it, and then essentially deserialize the object into a device reading, and then we're going to add it to a container in Cosmos DB that's optimized for writes, which is fairly straightforward. I'm just going to do a bit of logging out there just to say that the recording has been persisted. And then my final function, I've got this Cosmos DB trigger. So essentially, I'm setting up the Azure function to read off the change feed that is happening to my write optimized container. Just go through all the different, it's going to listen to it, process it, put it into this read-only list. And then for each document within that list, we're going to take it and then persist it to my read optimized container. Now, throughout all my functions, I'm using constructor injection. So in my trigger events, I'm just injecting my Event Hub client. And then here, I'm injecting my Cosmos DB client and also creating an instance of my container. So rather than creating a static client for each function, I've just instantiated a singleton object here for my Cosmos DB client, and then just which allows all my functions to share that Cosmos DB client. So let me kick this off, make sure it starts. This is the nerve-wracking part of the presentation, making sure my demo actually works. I did the whole, if anyone here's from the, okay, cool. All right, I'll explain that joke later. Sweet. So my function is now available to start. So I'm just going to send that off. I'm going to generate some events. Hopefully it's not going to complain. Sweet. So all my events are being written to Event Hub, being persisted to my write optimized container. And then I've got my materialized view. So I'm using event sourcing here to really try and not really change the data, but then just change the, or just pass data from my Event Hub all the way through to my read optimized container. So I've just generated about 100 events just to keep it short and simple. So here I am in my Azure Cosmos DB database. So I've got 3 containers here. So my, what I've called raw reading, so my write optimized container. So I've got all my events from earlier and also the ones I've just generated now being persisted here. So we've got some that have been some recordings for readings that are located in South America, United Arab Emirates, Japan, etc., etc. And essentially, this is petitioned on ID. Now, I won't go too deeply into petitioning in Cosmos DB, but essentially, there's no idea of primary keys in Cosmos DB. We use petition keys in order to distribute our data, and we might what value and what property we choose for our petition key depends on what we what type of queries we might perform and what type of workloads, specific containers we might want to optimize our containers for. So this is for my write optimized query. And then I've got my materialized container here, which I've petitioned on locations. So as you can see, it's all been petitioned by different locations. So if I just wanted to opt to write a very quick query, say if I just wanted to get all the readings from devices from New Zealand, which is where I am right now. And then I can just return that very simply. So depending on the type of queries, we might choose a petition key that we might perform a lot of queries against. But essentially, this is just a very simple way of getting some raw events from Event Hub and then persisting it to Cosmos DB and then doing a little bit of event sourcing, a little bit of query optimization across different containers using Azure functions. Now, let me see if I stop that. I think that's, let me just go to this change feed one. So setting up the change feed in Azure Functions is really, really simple and really straightforward. So here I've got my Cosmos DB trigger. I've specified the database name that I want to listen to and the collection within that database that I want to listen to in terms of creations and updating. I've specified my connection string setting. And then I've got something here called a least collection name. And this just essentially acts as a checkpointing for our change feed process. So we can create these lease collections if they don't exist within our functions. But then we can also specify the time, just trying to remember okay. So we actually specify when we want to write, when we want to listen or process changes to that have happened within our container. So we can start right from the beginning, or we can start from a specific point in time. So it's a really simple way just to configure the change feed within Azure Functions to meet our needs. Cool. Let me just go back to my slide. Just swap that. Cool. Okay. So that was just a really, really quick demo on showing you how you can actually use Azure Functions and Cosmos DB together to build some really interesting event-driven applications. If you want to learn more, I really recommend checking out the Microsoft Learn website. There's some fantastic courses on there for both Azure Functions and Cosmos DB, and there are some that work do lessons with them using them together, which are really worth checking out. Check out the documentation for both if you wanted a bit of a deep dive on both of them in isolation. The Cosmos DB team have come out with a bunch of deep dive labs, which is, I think it's 2.5 days or 2 days worth of content that go really, really deep into the nitty gritty stuff of Azure Cosmos DB. It's a really extensive subject, and it's a little difficult to try and encapsulate all of it within half an hour. So if you want a deeper dive into what Azure Cosmos DB is, I'd really recommend checking out those deep dive labs in the that have been created by the Cosmos DB engineering team. If you want more of an architectural overview and architectural guidance for Cosmos DB, I check out gotcosmos.com. They've got some really simple, straightforward guidelines of different scenarios and different situations that you might want to use Azure Cosmos DB in. And if you want more Azure Functions learning, I'd really recommend. So last December, they did 25 days of serverless. So each day, it wasn't just limited to Cosmos DB bindings or working with Cosmos DB. So the Azure Functions team came out with 25 days worth of challenges using different types of bindings, different types of technologies. So if you wanted a more hands-on approach in learning Azure Functions, or you just want to check out something cool in your spare time, I'd recommend checking that out. Thanks for listening. If you have any questions and you can't think of them right now, if you just want to catch up or just want to shoot me like a random question whenever, feel free to check me out on Twitter and just message me or just at me. I also will share the slides and the demo to this presentation on my GitHub as well, and I'll tweet out when that's available, or I've just mentioned something in the Discord channel as well. So with that, thank you so much for having me. Any questions?
All right. Well, Will, thank you so much for that, and congratulations on your demo actually working. I don't think I've ever been able to give a live demo without a significant number of problems. So
there have been times where I've been working with event hubs, and sometimes events won't be processed. So it'll just kind of sit there. So one like generic piece of advice for developers I can give when working with event hubs and Azure Functions is make sure you're using up-to-date versions of your SDKs, because they do come out with patches all the time that deal with these little problems. I definitely recommend checking out the Azure Functions GitHub issues list. Lots of developers some developers might encounter the same issues. In fact, for this demo, when I was preparing for this, I was actually having a little bit of trouble listening to events on my event hub. And I'd set everything up and I was just like, why is this not working now? And I was missing a library. Which is just sort of like a small, like little thing where you just think, oh, okay, that's slightly annoying. So definitely, use a lot of logging when you're developing. Try and see what's going on, and then just refer to those GitHub issues and just make sure that you're up to date with everything. Because you can get caught out by just little things like that. Yeah.
Yeah, those are the worst. With the things you just bang your head against the wall, and you're like, "What? Why is this not working?" And it's like a comma in the wrong place. All right, so I'm not deeply into Azure. I use AWS quite a bit, so I always love watching these talks and see what's possible, with other clouds and what other people are doing. So, question for you: how do you deal with infrastructure as code?
So at my workplace, we use Terraform.
Okay.
I know that even though I'm not hugely, I think I'm like the opposite, where I haven't had too much experience of AWS, but I think Terraform has a bit more of a sophisticated and established relationship with AWS. I think we're still starting to see some parity, but we use Terraform at work. I use Terraform in my own personal projects as well. I'm not a huge fan of ARM templates. I'm just going to leave it at that. But yeah, Terraform is the way that I usually work with provisioning infrastructure. And also, there's also PowerShell as well. So with Cosmos DB specifically, they have a really, really nice PowerShell module that you can actually provision. So you use Terraform for, say, your account, and then you've got databases and collections living inside that account. You might not use Terraform for that, but you use PowerShell, or it's got a nice REST API as well. So yeah.
Nice. All right, cool. All right, so then one last question. So you mentioned partition keys, and you were running some queries in there. I'm very familiar with DynamoDB, a NoSQL database. When you're building partition keys for Cosmos, when you're running those where clauses, does that have to be on an index, or is there the ability to sort of search unstructured data in a sense?
You can search unstructured data. It's just in terms of optimizing it, the way that you provision throughput in Cosmos DB. So say with indexing, everything is indexed automatically, but you can manage your indexing properties. So you can specify within your JSON document, okay, I know that these properties are always going to appear up, index on those, or partition on those. And that's one way that you can reduce the amount of request units or throughput that you're actually using when querying those documents. So you can do a where clause on an unpartitioned or an unindexed property, but there is a performance cost, and there is also a little bit of financial cost depending on what type of queries you're going to be executing on your documents.
Makes sense. Awesome. All right. Well, thank you so much. It was a great talk. You put all your contact information there. If people have more questions, hit up the Discord channel or reach out to Will directly. We are actually running a little bit early. So I think what we're going to do is at about maybe 40 past the hour, we'll start the next talk instead of 50 past the hour. So Will, thanks again. We'll take a quick break and we'll be back at 40 past.
Thanks for having me.
Hey everyone, welcome back. This is our last talk of the night, morning, afternoon, depending on where you are in the world. This is a great talk we've got coming up from Denis Bauer. She is a principal research scientist, and this talk is about serverless in the fight against COVID-19. So very timely talk.
Hello everyone, and welcome to my talk. Today, I want to talk to you about how we use serverless technology in order to fight COVID. Now, in the fight against COVID, we observed that data and technology has become as vital to the healthcare system as the clinicians themselves. Now, this is a bold statement, so let me backtrack a little bit and introduce the research organization that I work for. I work for CSIRO, which is Australia's government research organization. At CSIRO, we're really passionate about translating research into products that people can use in their everyday lives. Now, one of our most famous products is, of course, Wi-Fi, which is now used in over 5 billion devices worldwide. Wi-Fi has also helped in developing another great invention of ours, which is the heart rehabilitation device, which is a mobile, or the first mobile assisted device to help people who had a heart attack recover, and it has improved the uptake by 40%. And this was before people needed to stay away from the clinic in person. Now, on a lighter note, we've also developed the Total Wellbeing Diet book, which is now on the book bestseller list alongside Harry Potter and the Da Vinci Code. So from that perspective, we have a nice balance between products that people need and products that people enjoy. Probably more on the needs-based side is what we did for the national response to COVID in Australia. So the eHealth Research Centre, which I'm part of, is the largest digital health initiative in Australia, and therefore was involved in a wide range of different responses to the crisis. One is to look at the dashboard, which we've developed for the state governments to look at the use of the hospital system. And here our modeling work was involved as well. We also looked at mobile and telehealth devices so that people do not have to come in person to still be able to receive clinical care. And of course, the most important one, or the most interesting one, in my biased opinion, is the genomics work that we've been doing in that space, which I'm going to talk to you a little bit more about as the talk goes on. So, with this, I want to tell you about 3 stories. The first one is around monitoring. How can we understand this virus better? The next one is around diagnostics. How can we detect the virus before it becomes a problem, before it spreads? And the last one is around tracking. Can we identify specific pathways that the virus is using so we can stop those pathways and stop the spread? Now, this is of course not a clinical talk or a biological talk, it's an IT talk. So therefore, I'll be talking about the serverless architecture that we used in order to achieve those 3 things. Again, let us backtrack a little bit so we're on the same page and talk about the disease itself. So COVID, which is the disease, is caused by a virus called SARS-CoV-2, which is an RNA virus. In fact, it's a coronavirus that is one of the largest RNA viruses in existence. It has 30,000 letters in its building plan, which is the RNA that makes up how it functions and how it replicates. It is an obligatory parasite, which means it's actually not a living thing. It needs to hijack your cells in order to reproduce. And it does that by attaching itself to a receptor on the cell wall and then injecting its genetic material into the cell, then hijacking your productive systems in the cells in order to build copies of itself, which then burst out of the cell, infecting other cells of the body and of course other individuals. So how can we fight something that is so novel, that you can't see? Clearly, we need to invent new things. And invention here is around diagnostics in order to detect it, therapeutics to treat it better, and ultimately vaccines, stopping it from spreading. CSIRO, together with CEPI, is involved in developing those vaccines. Specifically, the Australian Centre for Disease Preparedness down in Geelong is involved in testing the vaccine. Specifically to do that, the virus goes into the high containment facility down in Geelong. There, the virus is replicated, and in fact CSIRO was one of the first organizations outside of China able to replicate the virus in sufficient quantities to be able to test its efficacy or test vaccines against it. So replicating the virus, the next step is then to sequence the virus in order to really understand its building plan and how it functions. Then animal models can be created, which then goes into the vaccine testing for safety and efficacy. Ultimately, it then goes into the first round of clinical trials, which is currently running, and then it can be rolled out to the general population. It's the same approach for vaccine development as it is for diagnostics and therapeutics. So what makes this so difficult? The problem with RNA viruses in general is that they evolve, they adapt to the human host that they are going into. So specifically, the COVID-19 has originated from bat, and before it jumped into human, there might have been an intermediate host, which I'm representing here by the question mark. But ultimately, it went into the human host. And once there, it adjusted to this new environment. And once it jumped from human to human, it adjusts even more to that by accumulating changes to the genetic material, which makes it potentially more transmissible, so easier to spread from person to person, or it could be a more virulent version, which causes a more severe disease. Now, those two questions are actually what we had in mind when we needed to analyze the genomic data from it. The first one is, does those genetic changes that it accumulates hinder vaccine development? And the second one is around, does it cause a more severe disease? So this brings us to the first story around the monitoring. So we developed a new approach that detects the changes in the genetic material of the virus. In fact, we think of it as taking the fingerprint of a virus, which is its unique profile that can be compared between one virus and another virus to assess how similar it is. So we used machine learning in order to map this information onto a 2D space, which is akin to a spatial map where the points between two locations is the spatial distance between it. We have here the distance between two virus isolates as the genetic distance between them, so how far apart they've evolved from the origin. Now we use this information in order to guide vaccine testing, and specifically which isolates should be picked in order to test the vaccine against. For this, we looked at the international initiatives currently developing vaccine or testing vaccines and looked at the isolates or the specific versions of the virus that they've picked and mapped them onto our 2D space and observed how well they represent the current spread of the virus. Good news is that at the moment, the vaccine isolates that are picked really represent very well the current spread. Now we need to keep an eye on that. And this is exactly what we've done with our webpage. So there's a webpage that looks at the genetic map of the virus, because there are new virus isolates deposited every day. In fact, there are thousands deposited every day. So this serverless architecture is actually looking at each virus that is newly deposited, calculates the genetic distance of it, and then put it on the web page for people to look at. So how is the actual architecture looking like? As I said, the virus is very large. It has 30,000 bases, which means in order to calculate this genetic distance, we need to have a specific function that does that. In fact, this function is too large to actually fit into a lambda function for now. We could parallelize it, but for now we've opted for a EC2 instance. So this is an AWS architecture, so a normal EC2 instance. But all of this is triggered by a serverless architecture. So whenever there is a new isolate deposited, a lambda function detects that and kicks off this process in order to analyze that particular isolate and deposit it on the web page, which then of course is updated through a serverless architecture. So in order to answer the second question, whether there is a more virulent version out there, we use an algorithm that we've developed previously for the application case of detecting the genetic or the disease genes for motor neuron disease, which is the disease that Stephen Hawking suffered from. So here the idea is that you take a control group, so a healthy group, as well as a group that have motor neuron disease, take their genetic material and then identify the changes or the specifics in the people with ALS compared to the people without ALS, which then ultimately can lead to new therapeutics and new diagnostics. So we use this algorithm in order to analyze the virus instead of human genetic material. So here we had 300 cases that had a more severe disease and 200 cases that had a milder version of the disease. And we observed, is there are there specific hallmarks in the one with severe disease compared to the milder disease ones? And what I'm showing along the length of the virus, I'm showing the spikes of locations in the genome of the virus that were more associated with causing a more severe disease. So the higher the spike, the more contribution it had to the disease. And as you can see there's the very much hotly debated D614G mutation, which potentially causes to be is more transmissible. It seems to potentially also have an influence on the disease severity. Now, I should say that this is hopelessly underpowered at this stage because 500 samples is not going to help us identify such a complex association question as this one, because there are comorbidities and the influence of the healthcare system that play probably a larger role on the outcome of the disease compared to the actual changes in the virus. So stay tuned for that kind of research because we're getting more data and we'll be repeating that analysis. So this brings us to the second story around diagnostics. So here, now that we have the potential of genetic material or genetic changes causing either more pathogenic or more virulent versions of the virus, can we build a diagnostic that detects that? And while we're at it, can we please do this from the comfort of our own home? So rather than sending our samples off to the pathology labs, can we have a handheld device that is lab-free to tell us what the virus is? So here we can fall back onto something that is called CRISPR. So CRISPR is typically used in genome engineering and personalized or revolutionizing medicine through gene therapy. And here we're working together with Westmead in order to bring this new kind of therapeutics to a specific liver disease where a genetic change in the liver, a genetic misspelling in the liver can cause severe disease. So the idea is to capsulate the CRISPR protein, which is a protein that is able to go into the cells and make changes to the genome at a specific location. So encapsulating this protein into a capsid that is addressed to a specific tissue of interest. In this case, the interest is the liver. So the CRISPR can go to the liver directly, and then the CRISPR protein can go to a specific location in the genome of the cells in the liver, correct the misspelling there, and hopefully this then corrects the genetic disease. Now, this kind of technology is now used for diagnostics as well. So rather than making a change to the genome, it is just recognizing the location in the genome that it needs to go to, and then has a reporting mechanism, a fluorophore, for example, or a lateral flow, which is akin to a pregnancy test, which then can be used in order to report that the CRISPR has indeed found the specific location in the genome which is indicative of this specific virus. So there are currently two companies, Sherlock and Mammoth Biosciences, which develop this kind of CRISPR diagnostics for coronavirus, or for COVID-19 specifically. Now, in order to be able to distinguish between the viruses, the location that it needs to go to in the genome needs to be very specific. It is basically a word that is recognizing in the 30,000 bases long genome of the virus. And therefore, this word needs to be absolutely precise and unique to the coronavirus, or the specific coronavirus, SARS-CoV-2, compared to other coronaviruses or flu viruses or any other virus out there. So this is a technology that we've developed called SORTE, which can recommend the word, the precise word that is differentiating between the different viruses, and still has very good recognition potential for the CRISPR diagnostics, for the CRISPR molecule to recognize it. Again, this is a web service and it's a serverless architecture. So here we implemented this split in the genome that I was referring to earlier, 30,000 bases. Of course, we need to chop it up into smaller bits so that a Lambda function can process the smaller bit and then feeds back the information to a larger database. So here we're using the SNS topic to fan out and oversee and collect the results back, and the DynamoDB collects all the information, which is then reported back to the user on the web page. So this brings us to the third story around tracking. As I said, there is this one genetic change, D614D, in the coronavirus, which potentially causes it to be more transmissive, so to be easier to jump from human to human. In fact, this particular version has arisen in Europe and is now the dominant version around the world. So the question is, are there any other changes that potentially has similar severe functionality, which is something that we need to be tracking? So in fact, here in Australia, we found a specific version that is specific to Victoria, which is one of the states here. We don't know whether it has any functional consequences. It most likely does not have. But it's an interesting element to track the origin of the virus, because it does not exist in any other state in Australia at the moment, and it's very rare around the world. So if you see that anywhere else in the world, or in fact anywhere else in Australia, it can be traced back to this Victorian cluster. So in order to facilitate questions like that, can you find what is the prevalence of a specific genomic change in the coronavirus? We developed a web page that allows exactly that, which is called the Beacon protocol, or the coronavirus beacon. It again is a serverless architecture that can take distributed data sets from multiple pathology providers or labs from around the world, in fact, in order to accumulate the data and then report back the frequency with which a specific change in the genome has been observed in the different data sets. So here, the interesting bit is that we don't require it to be consolidated into a central database. The data remains flat files in the different locations of the pathology provider, so they can control the ownership of it. All they need to do is register that bucket with the central component that we operate, and then they can revoke the permission to access it at any time without the system falling over. And still it's able to collide all that data together in order to report this vital information around what is the prevalence of this particular change or the genetic change around the world. Another point that I want to raise is that Gardner was saying that in a post-COVID world, building for resilience is more important than building for efficiency. So we observe this as well, in that our technology is still distributed through a digital marketplace. So we do not rely on people physically to go from place to place in order to advertise it. It is there. We don't require people to go into other labs in order to install it, because the installation is automatic. And we don't need people to go around and record the quality of it, because the quality is automatically ensured. And this is sort of the beauty of the online marketplaces, in that you have a global marketplace where everyone can deposit their digital product, and the client can go through this offering, pick the one and install it akin to an app store on your tablet or phone, and it automatically deploys into the account of the client that want to use it. So this gets around the issue around data privacy and ownership, because the compute goes to the data. So we've done this for our genetic algorithm that is analyzing the motor neuron disease, Variant Spark, which is currently on the AWS marketplace. And in fact, it was the first product from a public sector organization to be on the marketplace in the health space worldwide. So this is great in that we can achieve that for Variant Spark, but for serverless, it is not available because the billing mechanism around it is not available yet. So this is definitely something that the serverless community should strive for to have as well. So to wrap up, the 3 things to remember is that there's a lot of IT technology that really has helped in the fight against COVID. So I think every one of us can be proud that we have contributed one way or another to this vital fight that we currently have at our hands, by either developing open source tools or pushing for the cloud technologies to be more resilient. Serverless in specific has helped a great deal because it can overcome the unique issues that are associated with a coronavirus around data privacy and data ownership, because here it does not require the data to be consolidated into a central repository, or it can cope with the massive spikes of workload that might be there, where one day there's no interest in a specific genetic location, but there might be a massive interest the next day. It also has opened, I think, our eyes to the resilient factor that we need to factor in when deploying our code. So therefore, a serverless marketplace is something that we definitely need. With that, thank you very much, and let's work together.
All right, everyone, we're back. I am here with Dr. Denis Bauer. Dr. Bauer, thank you so much for that talk. I will say, watching some of that about the possible mutations of COVID-19 and so forth, I probably am not going to be able to sleep tonight, but Otherwise, it was a great talk. I appreciate it. I do have a couple of questions. You showed a few of your serverless architectures, and they're interesting. You didn't go into a lot of detail with them, and I'm just curious. They're pretty interesting and complex. Is that something that you were able to just come up with right away, or did you have to go through some experimentation to sort of get those workloads figured out?
Yeah, certainly there were experimentations involved, but I think as Adrian pointed out earlier today, these serverless is great for building blocks. So therefore, we figured out the individual components in our previous architectures. So for example, the fanning in and fanning out element of the architecture. We had that from way back when we developed our very first application, GT Scan. So therefore, this was a building block, a Lego block that we can just rip out of that one, stick it into this one, and off we went.
Great. So you were able to use those same patterns, just had to sort of replace some of the processing and things like that.
Yeah, that's exactly right. So it's interesting in that there are so many patterns out there for typical application cases, but for research, they don't quite work. So therefore, we did have to develop new patterns that are research-specific patterns, and therefore, it will be great to have a marketplace or an online library of those research patterns, so people can share those things as well.
Yeah, and so that's another question I have. So you have all these research scientists, and I know you're getting more and more, especially when you're talking about genomics and things like that are just getting that require massive data processing, getting into the cloud and being able to use some of the parallel compute and stuff is becoming really, really popular. But is moving to serverless though? Did you have to retrain your whole team? I mean, what's the learning curve for your average sort of data scientist to just, or I guess, genomic scientists or whatever, to just kind of get into using serverless technology and be able to sort of harness that power?
I mean, on the bright side, the research community is still very much behind. The high performance compute facility is still a pinnacle, and not everyone even uses that. So when I say bright side, there is not much training involved because people hardly use the cloud to begin with. Right. Therefore, whether they jump in and learn the lift and shift as the first one, or whether they jump in and go straight to the forefront of using serverless, that's basically what we do. We bring them on board, and rather than having to convince them that serverless is the right way in the cloud, this is the only way they know. So there's the cultural piece around it, I think.
All right. Well, I like that approach. Serverless first. It sort of dovetails from Adrian's talk to yours. So thank you, Denis, so much for the talk and what you're doing at CSIRO. That is just absolutely amazing. So thanks again. Really appreciate you being here.
Thank you so much for the time. It's always a fantastic community to come to and learn new things. I definitely did today. So thank you.
Awesome. Thank you so much. All right, everyone, that is the end of our talks today. So I want to just, before we wrap up, I do want to thank our sponsors, Epsagon, Stackery, Senzo, and Thundra. And I have with me a very tired but very excited serverless virtual crew. The planning committee here. So we got Gunnar and Emra. It's the floor is yours. What do you want to say to the wonderful serverless?
So, it's now 6 a.m. here, and the sun is just rising. And we started at around 2 a.m. for me. But when you think of that, what we are doing is a serverless community all around the globe. It actually works to stay awake and just to share the knowledge here, because we are the people who are supposed to be in airports, drinking beers while waiting for our next plane. But now we are all got stuck at home, and when we first think about it, hey, we should do something virtually around the globe, and we made the first event in the America time. Now we are in the APAC region, and I'm really glad that we are actually traveling the world in this way and just continue to share knowledge. And like it will continue. Next time we will be in the Europe time, and like we will again like have the awesome speaker lineup as we do have today and the last event. And I will be like I'm actually very, very glad to be part of this and just just to share the knowledge and like meet with new friends even if we are at home. So thanks a lot to all the sponsors, all my organizing committee, and Farah, Gunnar, and you, Jeremy. Like, I cannot think of a better host. Like, I believe, like, stay with us forever, I can say.
Well, I appreciate that. Does anybody else have any closing words? Just a lot of head shaking. Okay, everyone, thank you so much for watching. Again, Epsagon, Stackery, Senzo, Thundra. If you want to give a talk, you can go to virtual.serverlessdays.io. There's an ongoing or an open CFP. So if you've got something interesting to talk about with serverless, go ahead and submit that. This is the replay of this will be available. It's on YouTube. So make sure you send it out to all your friends and colleagues and anybody who's interested in serverless. We are going to wrap this up, and we will see you on Twitter and in the serverless world. We'll be there. So thank you very much, and we'll see you all soon.